I hope now the audio and the video is available perfectly, right? Okay, thank you. So basically, yesterday we had talked about the continental drift theory, and there we had had a conversation about what this continental drift theory was, how it was arrived at, what were the evidences that the theory was based upon, and also the reasons and the assumptions made by Alfred Wagner in order to prove his theory, and also the reason why why is the fact that continental drift theory was rejected. We also took a look at how to write answers in geography with the help of the question that we approached. Now, the same template we shall be following for the rest of the question series as well. Now, after that, we had started the discussion for the convection current theory, which was provided by Arthur Holmes. Now, in the convection current theory, we discussed about the transfer of heat from the portion in the interior of the earth to the surface with the help of the convection currents. Now, majority of these convection currents are driven from the Gutenberg discontinuity, and they drive through the entire portion of the mantle. Whereas sometimes the convection current is also to be generated from the region of asthenosphere, but for the majority of the times we'll find the convection current driven from Gutenberg. Now here we also discussed that when you have a convection current in place, it can have varied impact on the land surface. For example, the regions which are experiencing vertical portion of the convection current, they can experience an uplift, or they can also experience a kind of a volcanic eruption. Then wherever you have the horizontal component, that can involve movement of the earth's crust, and wherever you have the downward component of the convection current, that can experience subsidence or the formation of a trench in general. That is what was postulated during the time of Arthur Holmes. Now, after that, we had initiated the discussion for the seafloor spreading theory, which was provided by Harry Hess. Now, as per the seafloor spreading theory, what the theory was? The theory was that in the oceanic crust, newer crust keeps on getting created while the older crust keeps on getting destroyed. And in the process of creation of newer crust, where does the newer crust get created? It gets created in the regions of mid-oceanic ridges. And that is where Harry has basically found evidences of active volcanism in the region around the mid-oceanic ridges, which indicated there is creation of a newer crust. Now, at the same time, Harry has basically also observed that closer you are to the mid-oceanic ridges, newer are the rocks, and as you move away, as you move far away from the mid-oceanic ridges, the age of the rocks keeps on getting older and older. So that is based upon these principles, he created the seafloor spreading, that you have the creation of an, or you have volcanic eruption in the underwater region, in the region of the mid-oceanic ridges, which will push the existing crust to the side. And as the existing crust is pushed aside, that leads to the expansion of the sea floor. So that can drive the existing continents away from each other. Now, this was a theory which had its own set of limitations. It had its own set of limitations in the sense it could not explain everything that it started to postulate. For example, this seafloor spreading did not talk about how is it that the other features of the seafloor did come into existence. This seafloor spreading talked about the fact that newer crust gets created at mid-oceanic ridges and older crust gets destroyed in oceanic trenches. So if that is the case, then the number of mid-oceanic ridges should be equal to the number of oceanic trenches that we have. But that is not the case. So this theory also had certain set of limitations. But nonetheless, this theory proved to be very helpful in the sense that it helped us attain the insights for the plate tectonic theory eventually. So here we had taken a look at the theory, the postulation, how that newer crust is created. So today, again, very briefly, we will be talking about how that new crust is created. And then we shall be focusing upon the plate tectonic theory in the meanwhile. So starting with, first of all, the observations that Harry has made. So he made a set or a series of observations. Now, if you take a look at the observations here, on the crest of the mid-oceanic ridges, cracks with continuous active volcanism was found, which means they were volcanically active, right? These mid-oceanic ridges, they were volcanically active. Now, they were volcanically active means you will have newer materials which are erupted, newer material which are thrown out. So imagine if this is the existing mid-oceanic ridge. Let's suppose here you have an existing mid-oceanic ridge underwater. Now here you have volcanism, active volcanism. That means materials, they keep on coming to the surface. So molten materials, when they will rise up here, when the molten materials will rise up here, those molten materials will begin to solidify. Okay. Now these molten materials will begin to solidify. Once they have solidified, now that is a solid flow, but here again after some time active volcanism will be observed. After all, that is where you have molten materials coming out. So after some time, the condition will be somewhat like this, where the crust which was created earlier, the newer crust, that is also pushed aside. And in the meanwhile, you have molten materials which emerge, and these molten materials then will form the newer crust. This process will continue, and as this process continues, you will find, or you will come across a situation where the older crust is pushed aside and the newer crust keeps on getting created. The older crust created earlier, that gets pushed aside and the newer crust gets created. Now here also more volcanic eruption, so more materials will be thrown out. So like that, the newer crust gets created at the region of mid-oceanic ridges, whereas the older crust keeps on getting pushed aside. Now this was what the seafloor spreading theory talked about. Now this seafloor spreading theory, as I told you, it did prove something. It did prove something, that how or where crustal circulation happens, that is the circulation of the crust. It also did prove that how, or it tried to prove at least, that if the continents, they tend to move away from each other, this can be the plausible explanation. So it had its set of advantages, but it had a lot of disadvantages as well. It did not go beyond the immediate ambit of what happens in the seafloor. It did not talk about whether there will be any movement within the continents themselves, or are the continents completely dependent on the oceans only. So these all intricacies Harry Hess could not concentrate upon. Now Harry Hess basically also analyzed the magnetic field lines of the rocks while carrying out his study. In order to map the ocean floor, he wanted to know about the age of the rocks across both sides of the mid-oceanic ridge. He wanted to be aware, and he wanted to be sure that what is the age of the rock on one side of the ridge and what is the age of the rock on the other side of the ridge. So that is why basically Harry Hess carried out a magnetic field mapping of the seafloor. And when he carried out the magnetic field mapping, initially did not make much sense to Harry Hess. Initially, this mapping exercise of the magnetic field. Now, when I say magnetic field mapping, understand how does it help us calculate the age of the rocks. Listen to this very carefully for a couple of minutes. You'll understand this. So here, basically, we have seen that planet Earth, that induces a kind of a geomagnetism, isn't it? Due to the movement of the outer core and the rotation of the outer core, planet Earth induces a kind of a geomagnetism. So you have a magnetic field line. Let's suppose this is the magnetic field line as of today. Now there, We have also talked about the possibility that, okay, rather than me telling, let me ask from you guys. This magnetic field line, can it change or will it be consistent? What do you think? Magnetic field line by the planet, can it change or will it be consistent? Perfect. Beautiful, guys. It can change. It can change very frequently and very easily. Now, hold on your horses for a brief moment and try to understand this concept. So, suppose today the magnetic field line indicate this characteristic. Now, how are the rocks first of all formed? The rocks in general, when they are created, how are they created? By cooling of volcanic matter, cooling of lava. That is why igneous rocks are the primitive rocks. So suppose today you have a volcanic eruption here, somewhere along these lines. Let's suppose in this part of the planet, you have a volcanic eruption. Now, when you have a volcanic eruption here, molten materials will come out of the volcanic eruption. Molten materials will start coming out. And these molten materials, they will start to solidify. Now, during solidification, what does happen? When molten material solidifies, you have each and every molecule and particle which slowly loses their energy and then they solidify. Right. Now, all these particles, all these molecules, as they are cooling down, they have enough time and they align themselves as per the magnetic field of the planet. So, all these particles, while they will be cooling down, they will be aligning themselves to the magnetic field of the planet, which is prevalent today. Now, by observing this magnetic field, we can get an idea about when this rock was created. How? So, the magnetic field of the planet has changed hundreds and thousands of times since its formation. By looking at a rock's magnetic field, we do know what was the magnetic field of the planet in the past. We can match it up and we can gain, or we can basically guess the age of the rock. So, just by looking at the magnetic alignment of the particles that the rock indicates, we are able to calculate the age of the rocks. Because let's suppose a rock has been formed, let's suppose 200 million years ago. Now, 200 million years ago, what was the magnetic field of alignment at that point of time? We do know that with the help of the computer simulations and the various prediction models, we are able to calculate that. So when we see a rock, let's suppose rock shows an alignment where all the particles are aligned in this way. And the computer simulation shows that the last time the magnetic field had this direction was 50 million years ago. So obviously, the age of the rock is 50 million years, isn't it? So, like this, by studying the magnetic field alignment of the rocks, we can gain or we can guess the age of the rocks. So, that is how many of the times age of the rocks is determined. So, let me write it down here also so that it is clearer to you guys. So, by studying the magnetic alignment of the particles of the rocks and comparing it to the Earth's magnetic field, one can calculate the age of the rocks. one can calculate the age of the rocks, right? So Harry has wanted to study basically the rocks on the ocean bottom. So that is why he carried out a magnetic field analysis of the ocean bottom. And when he carried out the magnetic field analysis of the ocean bottom, there he found out that the rocks in general, let's suppose this is the seafloor bed. Now, there he came across the fact that the rocks indicated varying magnetic field. It was not similar, which meant that all these rocks were formed at a different time interval. So basically, while he was studying this, he found out that each of these rocks or the rock bed indicated a changing magnetic field in a few distance. Right. Now he did not know what to do with this information initially. That I have mapped out the magnetic field of the ocean floor on one side of the mid-oceanic ridge, and it all indicates different type of magnetic pattern, which means all of these would have been created at different time period, not at the same time period. So it did not make much sense to him. So what he did was he matched it with the magnetic field of the rocks on the other side of the mid-oceanic ridge. A mid-oceanic ridge will have two sides, this side and this side. So first of all, he was looking at only one side. Then after that, he had a comparison with the other side also, other side of the mid-oceanic ridge. Now that is where he found something very startling. When he looked at the other side of the mid-oceanic ridge, he basically observed that there is a kind of a similarity. Similarity in what? Similarity of the fact that as you move away from the mid-oceanic ridge, there's a similarity in terms of magnetic field. So here he found a similarity in the magnetic field on both sides of the mid-oceanic ridge. Okay, this was your mid-oceanic ridge. Okay, this is the ridge here. And then basically he found out that as you move away from here, as you move away from here, basically equidistant that you are, at the same distance you will come across the same magnetic field, which indicates that this rock and this rock would have been created at the same time. This rock and this rock would have been created at the same time. Same is the case with this one and this one, and so on. So these rocks would have been created at the same time, which basically indicated that as you move away from the mid-oceanic ridge, you get older rocks. Closer to the mid-oceanic ridge, you have the newer rocks. And basically, newer crust is created and getting pushed on both sides of the mid-oceanic ridge. So by this, with the help of the study of the magnetic field, he was able to guess and he was able to calculate not only the age, but to find the similarity of the rock structure found across both sides of the ridge. This is what he named as, or not what he named as, but this aspect of studying the age of the rocks by calculating the magnetic field and comparing it with the past magnetic field of the planet Earth, that is what is referred to as paleomagnetism. That is what we refer to as paleomagnetism. So with the help of paleomagnetism, he was able to indicate the similar age of rocks on both sides. Okay. Vivek, is the age of rock approximate on nature or exact? It is a very logical kind of answer. Always it will be approximate. It is never going to be exact. Swapnil, what is it that you are unable to understand? Let me know. And it means that Mithun, it means that magnetic field line will align in proper direction. Then we know by computer that direction. Yes, while the rock is forming, it will align itself in a certain direction. The particles will align themselves in a certain direction. So when we take a look at an old rock, we get the idea of that direction, and with the help of computer simulation, we get an idea about when did planet Earth have this alignment of the magnetic field. Okay, and we will come to the limitations of seafloor spreading theory. Lakshmi, please have patience. We will come to it. We are not escaping that. Pinto, presently, if the magnetic field of Earth is changed, then rock should also follow the same. No, the rocks which have already been formed, how will they change the particle alignment? It is the rock which is getting solidified from molten form. They will have the ability to change the particle alignment, isn't it? Not the rock which has already been formed. The rock which has already been formed is a hard solid. There you won't be able to experience any kind of change in alignment. Okay, is that understood, Pinto? How did they find out the Earth's magnetic field back in the 1900s? So we had the simulations, we had the kind of calculations based upon how frequently the magnetic field changes depending upon the rotation of the core. So that detailed information has been available. Okay. Kishan, magnetic field is also shifted place to place frequent. That is what I told you. Magnetic field changes almost has or changed almost hundreds and thousands of times since the formation of the planet. And what you are talking about shifting from Alaska to Siberia, that happened in 2020 itself. Around May of 2020 is when this event happened, when the magnetic North Pole shifted from Alaska to Siberia. Aarti, yes, the age of the igneous rocks are calculated in this way. Mithun, in every ocean there is a mid-oceanic ridge. Yes, I'll show you the mid-oceanic ridge also. As per the seafloor theory, do trenches have old or new rocks? Yatindra. So trenches are where the older crust is consumed. So it will have the older rocks. Swapnil, let me know what is the issue at hand, as the class is getting reconnected every 2 minutes. Okay. Check your internet connection, get it reconnected. Okay, Ashwant, ridges are like small mountain like structure continuously folded. Yes. And how will we know about the past data of magnetic field for comparison? That is something we get to know by comparing it with the computer simulations. Depending upon the planet's rotation, the speed has also been changing across the history of the planet. So by keeping all that factors into consideration, we get an idea about the changing magnetic field. uh, why does paleomagnetism doesn't make sense to him when he study one side? Because, okay, so see, if you are only looking at one side, the changing magnetic field will give you what idea? Nothing. But when you compare it to the other side, that is when you gain an idea that there is a kind of a mirror reflection in terms of magnetic field. There is a kind of a replication, which means the crust is getting created in this place and the older crust is being pushed aside. How many trenches created? We have many trenches across the planet there, and many small and major ones. We'll come to how these are created so you get a better idea. How to calculate age of rocks? There are multiple methods to calculate age of rocks. One is carbon dating, where you use the C14 carbon isotope and its half life to measure the age of the rock. Other can be with the help of paleomagnetism, where you find out the rock's magnetic field alignment, you compare it to the planet's historical magnetic field changes, and you get an idea about the age of the rocks. Okay. Paleomagnetism means the change of the magnetic line while the crust creation. Am I correct? No, Ashwant. Paleomagnetism is calculating the age of the rock, studying the age of the rocks with the help of studying or by studying the magnetic alignment of the rocks. Okay. Is there a possibility to repeat or to have the same alignment of Earth's magnetic field after a few thousand years? It is possible after a few million years that it can get repeated. So, there you can narrow it down, right? You will have a condition, let's say, that this magnetic field existed 50 million years ago, 250 million years ago, and 1 billion years back. So, you have narrowed it down. So, accordingly, you can calculate or you can guess the age that this rock would have been formed 50 million years ago, because if nearby rocks, let's say, are created 40 million years ago, then there is no way that a rock in between is created 2 billion years back, right? That is how you come to the conclusion. When rock changes to another type, can we see difference in magnetic alignment of the particles? When it changes into metamorphic rocks, oftentimes those changes, they are basically diluted, then you cannot see it. Okay. What does the impact on rocks due to magnetic field? On the rocks, basically, as the rocks, they start to cool down, igneous rocks, from liquid form to the solid form, as it begins to cool down, all the different particles, they will align themselves as per the existing magnetic field, and then they will cool down. So they will always leave a sort of an imprint about the magnetic field. Excuse me. So these rocks will always leave an imprint about the magnetic field when they were created. Okay. Yes, Vivek, that is correct. Since the magnetic field changes with time, why the magnetic alignment of rock didn't change as per today's simulation? How is it as per million years ago and not today? Like how it didn't change? If the magnetic alignment changes, see, when will the rocks have, so if I pick up an existing rock today, will it indicate to me the existing magnetic field of the planet today? Absolutely not. When the rock is solidifying from a liquid form, it is at that stage where the particles, they are cooling down. Those particles will have an alignment as per the direction of the magnetic field. So if this is the rock, if I find out or if I study the magnetic field, it will indicate to me when it was getting solidified what was the magnetic field of alignment back then. Okay. Biswajit, how the magnetic field is created by dynamo effect of outer core. So you already know about dynamo effect, my dear friend. So I think you should know the answer to this as well, or otherwise you have read it somewhere and then you are mixing and matching it with the session. So if you already know this, kindly don't have the question again, because please understand we are already going behind. But having said that, I will entertain this query one final time. And that is, as the outer core keeps rotating, there you have the presence of iron and nickel ions. So these iron and nickel ions continue a kind of a circular motion, a spiral motion. And that is when, as they are moving in a spiral manner, there is a generation of a magnetic field indicating the same behavior as you observe in a kind of a bar magnet. Okay. How and why the rocks get destroyed near the trenches and then where it goes. Please understand, this is a theory which was not accepted completely. This is not the final theory. Just understand what this theory is trying to tell you about. Don't think about it that what is the reality as of now and what this theory is talking about. It doesn't make sense. This theory is of early 1950s. After this, you had the evolution of plate tectonics. So don't worry about where the rocks will go, etc. We'll come to all of that. Don't worry. Okay. Right. So now we continue. with the limitations of the seafloor spreading theory. So when we talk about the limitations, seafloor spreading theory has got certain set of limitations. For example, it does not explain the features that you end up finding on the ocean floor. You have no clue of the features as per this theory, how sea mounts are created, how other features are getting created. You have goyards, you have other kinds of ridges, all of that, how they are created. This theory does not talk about that. Then it does not talk about the movement of the continents, in the sense it talks about the movement underneath the oceans, expansion of seafloor underneath the oceans, but it does not talk about the fact that whether there is any such force, any such movement occurring underneath the continents as well. So that is something which it is silent about. It does not speak in terms of lithospheric regions, that which are the portions which end up getting created, the new portions getting created when seafloor spreading, or Harry Hess, when he talks about the newer crust getting created, what layer of crust is getting created, what region of crust is getting destroyed, that has not been specified by the seafloor spreading theory. Okay, so this is basically the limitations. Another limitation is, as per the theory, if you take a look at it, then newer crust gets created at the ridges, older crust gets destroyed at the trenches, oceanic trenches. So if this theory was to hold true, then for every ocean you would have the simultaneous presence of ridges and trenches, because the surface area of the planet is consistent. It is not as if planet's area and planet size is increasing with the creation of the new crust. That means every time that there is a creation of a new crust, older crust must be getting destroyed somewhere. That means every ocean should have some or the other oceanic trench as well. So that is not to be found. So this is another limitation which seafloor spreading does not end up explaining. It does not explain about the features even on the continental areas. Okay. Now, here, if you take a look at it, these are your mid-oceanic ridges in general. These are the oceanic ridges. Now, when we talk about the oceanic ridges, here observe the light blue areas, all these areas, right? All these areas are the ones where the sea floor is getting expanded. All of these are the regions where the sea floor is getting expanded. So that is what is your oceanic ridges. This is where you have the creation of a newer crust. Creation of a newer crust. Okay. So that is basically the aspect. Now, what is a ridge overall? Ridge, when you see in this image, I had presumed that we all have an idea of a ridge, but I don't think every one of us present here has an idea of a ridge. So ridge basically is a continuous feature like a chain or a chain of a mountain, which has got an elevated form. Elevated form. It is not exactly a hill, it is not exactly a mountain, it is an elevated landform. So here you have volcanic activities which are observed underwater. Okay, so here if you take a look at it, this seafloor spreading observed by Harry Hess corroborated the fact that the continents can move apart. How? By expansion of the seafloor. By expansion of seafloor. Yes, Vedshri, that is a correct conclusion to me. Now, it formed the basis of the plate tectonic theory moving ahead into the future. So, overall, when you take a look about the seafloor spreading theory, so it was the first comprehensive theory to talk about the movement and formation of the seafloor. Simultaneously, other scholars such as Mackenzie, Parker, Morgan in the 1960s, they developed a more comprehensive understanding about the movement of different parts of the Earth's crust and the related formation. All this was later utilized to form and formulate the plate tectonic theory. So now let us come to the plate tectonic theory. Let us understand each and everything in detail, how these ridges are created, how the trenches are created, how the movement actually happens, why the movement happens, where is it that the movement is happening as of now. Let us understand all of that by looking at the plate tectonic theory. So what is the plate tectonic theory? So when we talk about the plate tectonics, so here tectonic is derived from the term tectonic, which basically means building, right? Not the building that you see on the streets, but the act of building. So plate tectonic. So plates are coming together to build any kind of a landform or any kind of a different feature. Now here, what does this theory talk about? This theory basically said that lithosphere is broken into plates, right? The lithosphere is broken into plates. Now, this lithosphere, when we say, what is lithosphere? We have talked about lithosphere earlier. If we remember, lithosphere is comprised of crust plus upper solid mantle. That is above the asthenosphere, that portion of mantle. That is lithosphere. Now that is divided and broken into various different plates. And these plates end up moving over the molten, semi-molten portion of the mantle. That is, they move over the asthenosphere. Move over asthenosphere. They continue to move over the region of asthenosphere. And all these plates, they move with relative or in respect to each other, relative to each other. And that is why they give rise to various different types of landforms. Why do they move? Which are the plates which are present? Do they move continuously or not? We will come to each one of this. But this is the very basic gist. Now, how did we arrive at this conclusion? This was basically worked upon by many different scientists. You had Tuso Wilson, who had a significant role to play. Then you had Parker, Mackenzie, Morgan, all of them. So, all of them used to present papers, research papers. And with the help of all these research papers, over a time span of 5 to 6 years, was when the finalization of the formulation of plate tectonics happened. So basically, 1900s has been an era of discovery, has been an era of scientific advancements in general. So throughout these 1900s, first of all, it is during these 1900s that we got to know about the internal structure of the Earth, the interior of the planet. And all of that happened because of our ability to understand earthquakes. So when the earthquakes would happen, we would gauge the earthquakes only looking at how much destruction is created or caused by the earthquakes. Later on, we came to an understanding that look, when these earthquakes happen in the interior of the planet, these earthquakes emit certain energy waves. And these energy waves travel through the interior of the planet. And then when you detect them, you get an idea about the regions that they are traveling through. So everywhere across the planet, multiple tens and hundreds of different observatories started being set up. Even above the oceanic areas, you had various ships which functioned as a mobile observatory. All of them for one single purpose: to observe the earthquakes wherever it happened across the world and map out all the information that we could get out of it. So, with the help of this, basically, we were able to finalize, we were able to chalk out the areas where the earthquakes happened very frequently. And the earthquakes did not happen in random places. The volcanic eruptions across the planet did not happen in random places. They indicated a kind of a similarity. if you map these regions, just to show you that how this mapping is provided for. So just to indicate to you, let's suppose I take you to the global distribution. Observe this image. This image is basically across the globe, the distribution of earthquakes as it happens, right? Observe the regions. Now you will find that it is not as if earthquake is evenly spread. It has got a certain kind of a pattern here, isn't it? You will find a certain kind of pattern of earthquakes. Also, if you observe the volcanic eruptions across the planet, that pattern seems to match, right? So volcanic eruptions are also happening, earthquakes are also happening. So based upon this, the scientists, they came to a conclusion. The scientists, that is Morgan, Parker, all of them, they came to a conclusion that, look, all these regions where the earthquakes are happening, volcanic eruptions are also happening. That is a region which might be weak in the earth's surface. That is why earthquakes are being experienced. That region might have a kind of a broken part in terms of the earth's surface. So that is how we got an idea about what the plates would be, what the plate boundary would be. And accordingly, the entire planet was mapped out. In the entire planet, it was mapped out that where you have the plate boundaries. So according to the delineation, then you had the classification based upon the size. So you had the major plates, major plates. Now, what were the major plates? The larger ones in size. For example, Eurasian plate, a major plate, very large in size. It is this Eurasian plate along with Indian plate which is responsible for the formation of Himalayas, something we'll take a look at today. Then North American plate, again a major plate. North American plate. Then after that, African plate, a major plate. Then after that, South American plate, a major plate. Then after that, Pacific plate, another major plate. Then after that, Antarctic plate, a major plate. Another major plate, which is getting broken into two, and in the few years from now, that plate would be broken into two. And that is, as of now, it is still considered a major plate. That is Indo-Australian plate. Indo-Australian plate. So these are your major plates. Why? Because these are larger in size. How did we get to know that these are the plates? Across all these plate boundaries is where you have the occurrence of earthquakes and in many of the cases even volcanic eruption. So by that we get to know what is the extent of the plate in general. Now one thing that you will notice in this image, in this diagram also, all the major plates have a combined presence of both the continental crust as well as the oceanic crust. It is not going to be, for example, Eurasian plate has got only continental, North American has got only continental, or so on. Both continental and oceanic crust, except the Pacific plate. Pacific plate is the only major plate which is completely oceanic. Other than that, all of them, they will have a combination of both continental as well as oceanic crust. Now, all these plates, they tend to move with respect to each other. Now, when the plates are moving with respect to each other, there can only be three types of movement. They can move towards each other, they can move away from each other, or they can move in a manner where they are neither moving away or towards each other, they are moving parallelly. For example, here in this portion, if you observe, the movement is parallel to each other. Here, if you observe, the movement is away from each other. If you observe here, the movement is towards each other. Here, the movement is away from each other. So that is why the movement can be only of certain kinds. Why do they move? We'll come to that very shortly. So basically, now we come to why do the plates move if they move at all? So the answer is in two words: convection current. That is the reason. So the reason, if you have to summarize, that is convection current. How? Let us understand that. Before that, again, a simple experiment that you can perform, you can look at your house as well. So again, just like yesterday, suppose here also, you take a utensil or a container, fill it with water. Okay. Now, on top of that water, keep two floating wooden logs, thermocol logs, anything. Two of them floating. Keep them together, A and B. Okay, you can keep them together in a still state, right? Then what you do is you start heating this particular water. After some time, what you will observe is that there is a generation of convection current here. The bubbles rise up. What do you think? All of us would have experienced this or the other kind of a scenario. What do you think will happen in this case? A and B will continue to stick together. A and B, will they move away from each other? Will they move in a separate direction, or will they not move at all? What do you think? Very good. A and B will move away. Because as this convection current starts to rise, eventually here you will have a convection current in existence. So after some time, you will observe A and B, they move away from each other. Now, why are they moving? Because underneath them, the water in itself is in motion. The water is in motion because of convection current. So A and B also, they are moving apart. Now, something similar is in existence in the region of the mantle as well. So if we have, let's say, the surface, or let's assume this being the surface, and here, let's suppose you have the crustal region. Or rather than the crustal region, now that we are aware of it, let's consider the plates themselves. Upper portion of mantle and the crust, that represents lithospheric plates. So let's assume above that you have the plates, and here in the region of the mantle, what do we have? You have a convection current. Because of the heat in the mantle, you have a convection current. Now what happens in this case? Suppose this is a joint landmass, a unified solid landmass. Now there's a convection current happening underneath it. So what will happen? Understand this again with a very simple example. All of us would have played with a plastic scale at some point of time in our life or the other. The plastic rulers that you use when you are a child, right? Or when you are in lower classes and you need to use that scale. Now, many of us would have tried to burn that scale as well, or played with fire with that scale. So if ever you would have noticed, now I don't advise you to start burning the plastic equipments at your house, that the faculty has basically recommended this. If you have done this, or if you have seen anybody do this, you would have observed this. So let's suppose you take a candle, right? You take a candle, and on top of that candle, place that plastic scale. Now, what happens? Will the plastic scale immediately start melting and drain like a liquid? No. Initially, what will happen is it will get heated up. It starts getting thinner in this portion. In this portion, it starts getting thinner. Then, as you start to pull it away, it will form a situation somewhat like this, where it will be stretched. It will get very thin in between. It will get very stretched and very thin in between, right? All of us would have seen that a plastic doesn't immediately melt like this. It becomes weaker where you are applying heat. You pull it off, it becomes very thin at that particular heated portion. Eventually continue to pull it off. What happens? It will rupture. It will break from here. Here it will break, right? Something very similar happens with the crustal region as well, and the lithospheric region as well. Let us understand how and why. So when you have the convection current which is provided, so in this portion, the convection current will provide that heat, the heat which was provided to the plastic scale immediately above the flame, that heat will be experienced by this region. Simultaneously, this region is experiencing the horizontal component of the convection current. Means what? There will be a kind of a pull, just like A and B experience that kind of a pull. Similarly, here also you will experience that kind of a pull. So it is getting pulled from both sides, and also here there is enough heat. So in the central portion, in this region, it will behave almost exactly similar to the plastic scale. So what will happen is here it will start to thin out. As the region is being pulled from both sides, in this region it will start to thin out. Okay. Now it thins out, means even from top it will thin out, even from bottom it will thin out. Now, suppose there is a nearby oceanic area or a water body nearby, a large sea or an ocean. When there is a creation of such depressed regions, always you will observe that water body from the nearby regions, they rush in, they come in, isn't it? So, this region, immediately, the water body from nearby will cover this area. And before you know it, this region will come underwater, which was earlier a landmass. But now, because of the convection current, this has weakened, this has thinned out, this has stretched almost. Further, as the convection current continues, that thinning out and that stretching will continue. Eventually, what happened to the plastic scale? Eventually, after immense amount of thinning out, this will thin out even further. It will get stretched, it will thin out even further. So it gets further stretched, and it will thin out, barely making the surface anymore. And the water body is going to become ever so expansive. Earlier, you had no water body here. Earlier, you had the presence of only landmass. Now, observe the water body is growing in size. After some time, as the heat is continued to be provided, this region finally ruptures. It breaks. And as it breaks, here, what will happen? As it breaks here, volcanic materials will start coming out, because now you have a gap. So volcanic materials will start rushing out underwater, and it will lead to creation of a newer crust, while the existing crust is pushed aside. Right? So a convection current which is present anywhere can lead to the breakage of the crust and the movement of the crust. So now the next question which should come into your mind logically is, how do we know where the convection current will be present? And for how long is the convection current present in general? So understand that why this convection current is present, first of all. So convection current basically is present due to the residual heat of the planet. Residual heat since the time of its very formation, isn't it? So convection current has been present since the time of the formation. The residual heat is trapped. So it can happen that sometimes, let's suppose sometime here a convection current is generated because of that release of residual heat. Now this will continue to release the heat as long as there is excessive present here. So it can be in existence for millions of years, for hundreds of millions of years. It can also happen that after, let's say, 50 or 100 million years, this convection current finally comes to an end because all the excess heat from that region has been expelled. Maybe another heated region develops here, and then you have new convection current here. Simultaneously, another convection current developing here. Simultaneously, another convection current developing here. So convection current develops and goes away depending upon the residual heat. Where is it that the residual heat comes into play? So as long as there is a convection current, the plates will be forced to move. Okay. So here, if you think about it, the plates can move only in a certain way. Ideally, you would think that the plates will always be moving away from each other, but that is not the case. Suppose I consider 4 plates or 5 of them. Suppose I consider 4 plates, A, B, C, and D. Now, if I have a convection current underneath this, right? Now, B and C will be moving away from each other. Now, A, regardless of whether A likes it or not, but B is moving towards A. Regardless of whether D likes it or not, C is moving towards D. So there is going to be a convergence here and here, and there's going to be a divergence in this part. Okay, so that is how, due to the same convection current, the plates can move away and towards the other plates. And this is how they can also end up inducing a parallel motion. For example, suppose here I have plates like this. North to south, I am indicating. Okay, this is north, this is south. And here I have a mid-oceanic ridge. So there is a divergence happening in this region. Okay, there's a divergence. Now here, this is going to move away, this is going to move away, this is going to move away, this is going to move away. Now in this case, A, B, and C, all of them are moving in the same direction, but all of them would be moving at varying speeds. So if you consider A, B, and B and C, they are moving parallel to each other, isn't it? So that is how you get a plate movement. We will study more about it as we take examples of where it is happening in the world. But overall, if you think about it, this is the movement, why the movement happens. Generally, because of the convection current which is generated in the mantle. Why is there a convection current in the mantle? Because the lower portion of mantle is much hotter than the upper portion of the mantle, due to which there is a transfer of heat through the movement of a convection current. Okay. Now, this is the example of how in an existing landmass, when you have application of heat from underneath them with the help of the convection current, observe that the land starts getting thinner. Eventually, water gets in from the nearby regions, and then eventually the land continues to get away, eventually forming a kind of a mid-oceanic ridge, creation of a new crust. A region across the planet where this has been observed, in the region of Arabian Peninsula. When you observe the Horn of Africa and the Arabian Peninsula, they are strikingly similar in terms of the shape. And that is because of this factor. The land has gone away. We will take a look at all these examples. Okay. So here we start basically with the types of plate movement that we have. So overall, the plates can have three types of movement. The plates can be moving towards each other. The plates can end up moving away from each other, or they can also exhibit a motion parallel to each other. So when the plates are moving towards each other, that is convergence of plates, right? When they are moving away, divergence of plates. When they are moving parallel, transform plates. Now, each of the plate generally will have both continental and oceanic crust. Now, first of all, we'll take a look at the convergence, then divergence, then transform, where it is happening, what kind of convergence, why it is happening. So, convergence. So, we have oceanic crust in existence and continental crust in existence. So, there can be three types of convergences which can happen. You can have the convergence of an oceanic crust with a continental crust. We can have a convergence with one oceanic crust colliding with another oceanic crust. We can have a convergence with one continental crust colliding with another continental crust. Okay, so we can have these three types of convergences, and it is these three types of convergences which actually end up happening. Let us analyze when, where, and what is the outcome of it. So we start with, first of all, the basics of convergent plate. Now, I will show you the image also so that it is easier for you to understand and think about it. So basically, if you think about this one, these plates, just to show you where that convergence is happening. So observe in this region here, western part of South America. Here you have a continuous convergence happening between the Nazca plate, which is a minor plate, and the South American plate. In this portion, if you observe the Pacific plate is going underneath the region of Eurasian plate and the region of North American plate. Here, Pacific plate is colliding with the Filipino, the oceanic convergence is taking place here. Here also you have oceanic convergence taking place, right? Observe here. Here you have divergence taking place. The plates are moving away from each other. Through the entire region of Atlantic Ocean, the plates are moving away from each other. This is the region of divergence that I was talking about. That Arabian Peninsula has separated from the region of Africa and water has come in. So Red Sea has been formed as a result of that divergence, right? So here we take a look at this convergence. First of all, we start with the basic convergence that happens. So when there is a convergence which happens, you will observe that some part of the plate starts subducting. It undergoes subduction. Some part of the existing plate will undergo subduction. Now, the part of the plate which undergoes subduction is lost. It is pushed into the region of the mantle, right? Where after reaching a particular depth, significant amount of depth, 160 to 200 kilometers, the temperature will be so high that the materials will start melting. So here, because a part of the existing plate is destroyed, this is what is also referred to as destructive plate margin. Always understand, whenever this convergence is going to happen, always it is the heavier plate which is going to start indicating a sink or a subduction. Always the heavier plate will undergo subduction. Always the heavier plates undergo subduction. Always. Whichever is the heavier plate, that will undergo the process of subduction. Okay? So let us understand this entire process. Let us understand with the help of an example, first of all. So here we start with the ocean and continental convergence. Let us start with the ocean and continental convergence. The example of it that we have just seen, that is here, for example, we will consider. Now, by the way, whichever examples that we are considering, guys, and as we move ahead in the portion of geomorphology as well as climatology, we shall be discussing about many of the places across the globe. As a candidate, it should be your prerogative, it should be your priority that, let's say, I don't know about that place, and it is very normal. There is no shame in admitting the fact that maybe I don't know something, right? If you admit that, only then will you be able to improve. So let's say we are discussing about a place in South America or North America that I'm not aware of. Don't get disheartened by that at all. Don't start thinking or doubting yourself ever. Immediately after the session, open up the atlas, look at the place which was in discussion, and automatically that is how you will expand your existing knowledge source. Always understand, because I have been getting certain set of mails that many of the candidates, they know more than us, so are we at a disadvantage and so on. Understand, even if someone knows more than you, they did not reach there from their birth. They have reached there after they have studied that. So initiate that portion of familiarization even today. You will be in a very good place, let's say only within 3 to 4 months. But you need to do hard work for that. So here, basically, suppose, for example, we consider South American plate, American plate, and Nazca plate. Okay. Now, South American plate and Nazca plate, they are colliding with each other. We have seen in the image. So here, let us suppose, now, by the way, Nazca plate, we have seen earlier, Nazca plate we have seen is what? Is an oceanic crust. South American plate is what? This part is going to indicate, the western part is going to indicate a continental crust, isn't it? So here, if we draw about it, if we think about it, so first of all, Nazca plate being the oceanic crust is going to be thinner. It is going to be very thin. Whereas the continental plate, that is the South American plate, that is going to be significantly thicker, much more thicker. Now, both of them are colliding with each other. Now, by the way, out of the Nazca plate, this is the Nazca plate, the thin one, and the continental plate or the South American plate, which one do you think will be the heavier plate? Which is going to be the heavier plate? Good. Very good. It is the Nazca plate which is going to be the heavier plate, because the oceanic crust is always going to be heavier. Why? Because of greater density of the oceans. Oceans have a very high density, oceanic crust has got a very high density, and the continental crust has got lower density. So that is why continental crust tends to have a kind of a flotation aspect. So here, when we talk about these oceanic regions, understand everything is going to happen underwater, kilometers deep of water. Okay, now follow this logically, carefully for just 5 minutes, and you will understand a significant portion of it. The thicker one is the South American plate. This is the South American plate. This one is the South American. Nazca plate is the thinner one. Okay. So here, this is what is the heavier plate. Okay. Now, when it is undergoing that convergence, Nazca plate is the heavier one, right? Despite being very thin, it is the heavier one because of very high density. So the heavier one is the one which will undergo subduction. The heavier one is the one which will start sinking below. Now, here you will observe that as both of them they get together, do you think immediately one portion will start moving down the other very smoothly? No. After all, even if we are drawing this on the image and with the help of a diagram, but you have to understand these are kilometers thick rocks that we are talking about. And these kilometers thick rocks, they will never be moving very smoothly with respect to each other. They will be hardly moving because there will be a force of resistance offered by the other material. Let's suppose this is the Nazca plate, this is the continental plate. As the Nazca plate will try to sink down, there will be a resistance offered by the other rock type. So it will not move significantly due to the resistance, but sometimes it overcomes the resistance and there's a sudden motion of sorts, right? Whenever this sudden motion happens, a lot of energy is released, and that energy shakes up the Earth's surface. That is what we refer to as earthquakes in general. Let us understand that. So, here, as this plate starts to move and undergoes that kind of a subduction, now the continental plate, which was nearby, that will not allow the subduction to happen very easily. So this will get deformed. This continental plate here, that will start getting deformed. And the materials at the continental plate here, if suppose this is the continental plate, as the Nazca plate is pushing in, these materials at the continental plate will start getting accumulated. So at the region of the continental plate, you will find that accumulation of materials happen because it is less dense, it is very thick, and you have the formation of a kind of a fold mountain. So this accumulation of materials happen in the case of the continental plate. And that will lead to the formation of a fold mountain. Here, meanwhile, this continues to sink down, right? Now, this is all happening underwater. Now, in this region, observe that there is a depth, right? A deepened portion has been formed at the ocean bottom. Now, this deepened portion at the ocean bottom, this is what is referred to as an oceanic trench, oceanic trench. In this case, the example that we are talking about, locate in the map later on, you will have the presence of Peru, Chile trench. Okay. Now, here, continental plates basically where you observe this fold happening, accumulation of materials happening. So, continental plates, they are very light. Think about it like a thermocol. Now, if you press the thermocol tends to accumulate in a way, right? It accumulates. So, that is how that accumulation leads to the formation of fold mountains. Example in this case, you have, in this case, the example is Andes. Right? Because they have been forced. So there is an accumulation happening here. Now, in this zone, at this portion where the two plates they are rubbing against each other, the motion is never going to be smooth. The motion is going to be haphazard, irregular, staggered in a way. It is going to experience significant amount of friction. Then suddenly it will overcome a friction and suddenly there will be some movement. Again, there will be a lot of friction for a long period of time. So whenever you have that sudden motion, energy will be released. A lot of energy will be released. So these are the places of earthquakes. High magnitude earthquakes. They are very common in this area. Then after this, here, now, as the materials they go down, now along with this oceanic plate, as the oceanic plate starts to subduct, some part of the water will also be able to seep down here, isn't it? It is not going to be that no, only waterproof elements can go into the mantle, so water is not allowed, there is a gatekeeper. No, some water will also seep there. Some amount of sediments, marine sediments will also seep there. Now, as it starts going lower, now a unique phenomena happens. This phenomena is basically when you have any object which is hanging down. Let's suppose you have an object or a plate, let's say like this. A plate is like this, let's suppose. Now, this portion of the plate will experience a greater gravitational pull because it is hanging down. If ever you have played with a toy train, there you will get a perfect analogy. So if ever you have played with a toy train, basically, toy train, when you keep it on the table, absolutely flat, right? Absolutely flat, no issues. You keep it to the side of the table, the edge of the table, and hang the engine at the lower end. Now, if the engine is starting to hang, you will observe slowly and steadily that will pull the entire toy train down. Why? Because the force of gravitation or the gravitational component is significant for the vertical aspect. So here also, as the plates they begin to come down to the mantle, there is an increased gravitational force which pulls the rest of the plate. So the overhanging portion of the plate that tends to pull the rest of the plate. And that is the phenomena which is referred to as what? Slab pull. That is referred to as slab pull. So here also, slab pull will be experienced. When slab pull is experienced, this portion which is overhanging will start pulling the rest of the plate significantly quicker. Right? Now, as it is moving down at a depth of around 160 to 200 kilometers almost, the temperature becomes high enough that the materials start getting molten. At the same time, the water which has seeped down immediately will get converted into steam and water vapor. Now that steam is going to have pressure, it is going to be light, it is going to want to come to the surface always. So here, the molten materials along with the steam, these molten materials, they will begin to rise up because they are lighter and they have so much amount of heat that they will continue to melt the materials along the way as they are moving up. So they will continue to push ahead, melt the materials along the way. All the meanwhile, more plate is sinking or subducting, meaning more molten materials are being provided. All these molten materials, they will rise up. After a point of time, they will be able to break through the surface and form a volcanic eruption. So here you will have the volcanic eruption. Volcanoes. Example in this case, take Mount Cotopaxi. Okay. So here, why is it that molten materials were created? Because as you go to a depth, as the materials, they go to a depth of 200 kilometers, 160 plus kilometers, they get into a region where it is very heated up. So the water and the sediments which have seeped in along with the oceanic plate, they will have a lower melting point as compared to the rocks. So immediately they will start melting. Now, as they start melting, as the water and the sediments which have come in, now they will start getting heated up, they will start melting, they will start to rise up. Because molten materials, that is liquid and gases will always exert pressure. So that gases will try to come up, being lighter in lighter in weight as well. Eventually all this will, because they have significant amount of heat, they will start melting the materials above them, and eventually they will crack through or break through the surface, leading to volcanic eruptions. So that is why whenever you have oceanic continental convergence, you will always end up finding volcanic eruption, oceanic trenches, fold mountains, all of these to be formed there. Now, fold mountains in this place has been created only because there's a continental plate. As you compress the continental plate, things begin to accumulate. Something similar is observed even in the Japan coastline. This is the reason that Japan experiences volcanoes. Example, Mount Fuji or Fujiyama. This is the reason why Japan is frequented by very heavy earthquakes, because you have a zone of friction. This is the reason why on the east of Japan you have a very deep Japan Trench and Kuril Trench. That is because that is where the Pacific plate is undergoing subduction. So wherever you have an oceanic continental convergence, the oceanic plate subducts, leading to the formation of these landforms. Okay, right? In the figure, lighter one is sinking. No, my dear friend Shijin, this is indicating the Nazca plate. That is the heavier one. This is indicating the South American plate. Okay. So it is always the heavier one which will sink. Barren Islands also has convergence of oceanic and continental plates. No, in that case, it is oceanic and oceanic crust. Rockies and Andes now stable or still converging. It is still converging. It is still converging. Okay. Is Mount Cotopaxi active recently? Not immediate recently, but then it has had an eruption in the recent past if you consider a few hundred years. Okay, and Kishan, where imaginary lines of plates isn't drawn, we can assure there is no earthquake. As in, where we don't have an earthquake, Kishan, please specify your question. Imaginary lines of plates, this is where the plates will start to melt. We can assure there is, where imaginary line of plate isn't drawn, we can assure that there is no earthquake. Okay, you are talking about the plate boundary or the plate margin. Okay, no, that is not always the case. Earthquakes can happen in other areas as well. They are frequented at the regions where you have the plate boundaries. Kaluri, is always when oceanic and continental plate converge, only oceanic plate subduction takes place? Always. Always the heavier plate will subduct. And which is the heavier plate in the case of oceanic continental? Oceanic. When you have oceanic convergence, the heavier of the oceanic plate will subduct. Always. Okay. For how many of us it is not clear that which is the heavier plate? Always understand that oceanic plate is going to be thinner, but still it is going to be heavier. Please don't get confused by size. Size is the most misleading thing in the entire universe. So here, if you think about it, let's suppose this is the, let's consider this example or analogy which we have talked about in second session also, but let's suppose we have forgotten this. Let's suppose you have a thin iron slab and you have a very thick, almost 5 times or 10 times the thickness, let's say thermocol. Out of iron slab and thermocol, iron slab is thinner. But if I ask you which is going to be heavier, always iron slab is going to be heavier. Why? Because the density is higher. Similarly, when we talk about the oceanic plates, the oceanic crust is thinner, but because the density is very high, it is always going to be heavier. Is Himalayas also formed due to this phenomenon? No. Himalayas is formed due to different phenomena. Okay, and then Pulkit means for volcanoes to occur, one plate should always be oceanic. In the case of convergence, yes, but there are other methods of volcanic eruption as well. Is necessary to have volcanoes at everywhere where this kind of a situation? Yes, everywhere where you have this kind of a convergence, volcanic eruption will occur. And Akula, molten materials. So as the materials, they start subducting, they go beyond the depth. That is when the materials will start to melt, because at the depth, with the increase in depth, the temperature tends to increase, what is referred to as a geothermal gradient. So as we move into the depth at a distance of around 150 to 200 kilometers from the surface, that is when the temperature is high enough for the water and the other materials to begin melting, and that is when the molten materials, they start rising up. Okay, Chimborazo will also be an example. Aconcagua can also be an example. Aconcagua is the highest peak of South America, so that can also be an example. Then why Andes is thick in between? Because the convergence is not going to happen at the equal rate everywhere. In some portion, when you are talking about tens of thousands of kilometers, some portion will have increased convergence, some portion lesser convergence. So that is going to be a part of it. Okay. Northeastern part of Africa, which is continuously moving apart from rest of Africa. So there also you have the formation of a fold, Amit. Correct. Okay, earthquake occur because various anthropogenic reason also, that is correct. And in last time you taught us that oceanic plate is heavier. Okay, my dear friend, today also I will teach you the same thing, that oceanic plate is heavier. Please don't feel betrayed by it, that last time I told you something different and today I'm telling you something different. I maintain the same perspective because it is not me who goes on and weighs the oceanic plate every time. It is because of a logical concept which is there. So anybody you ask, they will all confirm to the same fact that oceanic plate is heavier. It is not a conspiracy that I'm cooking up. Oceanic plate is always going to be heavier because of greater amount of density. Okay. How Himalayas are fold mountains, we'll come to it. We'll come to the Himalayas, we'll come to earthquakes, volcanoes, everything, we will come to it. As of now, the questions I should restrict to the portion that we have covered till now. Is subducted crust melt more easily? Lakshmi, basically, when it goes to a depth, that is when the temperature will increase, and that is when it will start to melt, right? So the portion which is subducting, only that will be able to reach a depth. That is why it initiates that melting. Okay. Nirbhay, I hope now you understand why volcanic eruption occurs. Lakshmi, you have another question of slab pull. Slab pull is basically when a portion of this plate starts to subduct, it then has got a tension or a kind of a pulling motion for rest of the plate. So that is a portion of the plate pulling the rest of the plate as it starts to hang down. So that is what is slab pull. Hariom, it will be subduct. Shallow fold mountain formed due to compression and compaction of accumulation. Yes, that is correct. Mariana Trench doesn't have the same formation, Anjali. And Arnab, you can call oceanic crust also. You can call oceanic plate also. That is a portion of oceanic plate. Abhay, do we need to by heart all the examples? No, Abhay, just understand all the examples. Eventually, at the end of the day, when you have looked at all the examples, automatically you will tend to retain them. You don't need to learn all of these. Okay. Indo-Australian plate is getting bifurcated into Indian plate and Australian plate. East trenches appear in only boundaries of ocean and continental plate convergence. Can it happen in oceanic convergence as well? Yes, correct. Okay, Mithun, I have given the answer to this. Biswajit, it means for volcanic activities, there must be an oceanic plate to subduct. As I told you, this is one of the reason. One of the reason for volcanic eruption. There are other reasons for volcanic eruption as well. Okay, why every year Himalayas height is increasing? Please let us come to Himalayas. Then we will talk about Himalayas, fold mountain, Himalayas, height increasing, Himalayas formed how. I understand anything associated with India immediately spikes our interest, right? If I'm talking about South America right now, nobody is interested. If I were to talk about, why Himalayas, what is happening in Kailash mountains, what is Ram Setu, I'm sure immediately everybody will be interested. And later on, you will be the ones who will be having a problem that world geography is not covered. We have only talked about India. So this is, first of all, let us concentrate on what is happening in the world. I will tell you the detailed formation of the Himalayas as well. I'm not running away anywhere. I will tell you about the aspect of the formation of Himalayas as well. Have patience, hold your horses. I understand it is very difficult to have patience, but try to have patience. That is the job you are going into. Okay. Yes, Mahima, Rocky Mountains are also formed in the same way. Bermuda Triangle, please don't take me there. I have no clue about what is Bermuda Triangle, what is happening in Bermuda Triangle. I have no clue about what happens in Kailash Mountains, etc., whether there is a divine intervention or not. And similarly, I have no clue about what is Ram Setu. And similarly, I have the same opinion for River Saraswati as well. So all these topics that you are seeking answers to, Bermuda Triangle, what happens in Kailash Mountain and Kailash Mansarovar, is there an individual sitting there? What happens in Ram Setu? What is about the Saraswati River? I have no clue about that. Neither is UPSC interested in that. If you want to quench your curiosity by that, you have endless number of YouTube channels which keep on floating these conspiracy theories. You are free to visit that. Okay. And in mountain formations, we have classification like fold mountains and so on. Likewise, do we have classification of volcanoes? Yes, we have a classification of volcanoes. And could please explain that volcanic portion again? Okay, for the final time, for the fifth and the final time, I'm going to explain again about the formation of this volcano. So basically what happens is one plate starts to go down. This plate starts to go down. The heavier plate will initiate the subduction. Now, as it goes beyond a depth of 150 to 200 kilometers, the temperatures will be very high. That is when the materials will start melting, and liquid is lighter than solid. Solid is heavier, liquid is lighter, gas is even more lighter. Because water has come in, seeped in, that water will vaporize into water vapor or a gas. So all this will try to come up because they are lighter. They will find their way, melt the materials above them, and emerge as a volcanic eruption. Okay. When the South American and Nazca plate converge, then why Nazca go down due to gravitational force rather than the South American plate? What do you think? Which plate should go down? The plate that we decide, which is having a good behavior, that plate should go down? Or do we have any other criteria for the plate going down? What do you think should be the criteria? If we were to decide the criteria for the plates undergoing subduction, what should be the criteria? The good plate, the larger plate, the more beautiful plate, that should undergo subduction? No. The heavier plate undergoes subduction. Okay. And I think all of us, we have forgotten what we have studied 2 sessions back. So I will write it down here. Always understand oceanic plate. I will write in capital letters. Oceanic crust is always heavier than continental crust. Okay. Now, before we get confused even more in this, remember this always. And another aspect I want you to remember is the fact that oceanic crust is thinner. Okay. Oceanic crust is thinner. So why will it be heavier if it is thinner? Because from our childhood days, we have seen anything which is bigger is going to be heavier. So I understand if this simply boggles up your mind that how can something which is thinner be heavier? That is why I've given the example of iron slab and thermocol. Why it is heavier? Because it has got greater density. Greater density. Is that understood now? That why Nazca plate will go down, where continental crust will go down, where oceanic crust will go down. Is that clear now? Or are we still having doubts in this? Clear? Good. So now we will move on to the next type of plate. Before that, we'll take a break. So we take a break and then we'll be back in how much time? Does oceanic and continental plate, Rahul, let me know if this is clear or not. Does oceanic and continental plate converge? No, there are other places of convergence as well. Yes, Kishan. Zealandia is a plate in the region of New Zealand where almost 75% of it is submerged underwater. So here we'll take a break. 10 minutes will do. Let's take a break for 10 minutes and then we'll be back in 10 minutes. Okay. We will come to the classification of volcanoes, Ashwant, then we will come to it. Okay, what will you do knowing about all of that now only? Are you seeking to skip the next class or what? So just wait for some time. We'll come to the volcanoes, we'll come to the classification. What are calderas? What are volcanic hotspots? What are mantle plumes? Why do we have the eruption in the region of Indian Ocean? Why we have eruption in Pacific Ocean? We'll come to it. Let's take it slow and steady at one point of time. We'll come to it. Okay. What is the role of water vapor in the convergence? Water vapor basically provides the pressure which pushes all the materials upwards. No, Pulkit, no. Okay. A confirmation about the audio, please. Okay. Divya will, let's take a look at all the convergences and then we will have a conclusion. Is it important to learn all the examples? Ideally, you should know about the various examples, and those examples will be helpful when you are writing the answers in the mains exam. Can we say that slab pull is one of the reasons for earthquake? Not always. One of the reasons, yes, but then there are other factors also. So now let us take a look at other type of convergence, that is when you have oceanic and oceanic convergence. Example of this is the convergence or the collision between the Pacific plate on one side, the Philippine plate on the other. So observe here in this region, you have the Pacific plate and the Filipino plate. So here you have a kind of a convergence between oceanic areas. So let us try to understand what happens in that case. So in this case, always keep one thing in mind, that which plate will undergo subduction. If you have two oceanic plates, which is the plate which will undergo a kind of a subduction? So always understand it is the older oceanic plate which is going to be heavier. The older oceanic plate is going to undergo the kind of subduction in general. Okay, so always understand older oceanic plate is heavier and undergoes subduction. Now, why is it that the older plate is heavier? So basically an oceanic plate, let's say, which has been created 50 million years earlier or 100 million years earlier than the other plate, in that situation, what happens? There is enough time for the formation of various sedimentary deposits on top of that plate. Various oxides will be formed. So overall, the ocean plate which has been formed earlier will undergo a lot of sedimentation in that period of time and will end up becoming heavier. So here when we take a look at the example of this, example we can take Pacific plate and the minor Filipino plate that we have. So if you observe here, the minor Filipino plate here, this will be another oceanic region. Okay, so Filipino plate. So in this situation, which is the heavier one? It is the Pacific plate which is going to be the heavier one. Heavier plate. Why is that the case? Because whichever is older is going to be heavier, and that is what undergoes subduction. Why is the older plate going to be heavier? Because the older one would have experienced, older plate has got thicker deposits, which makes it heavier. Okay. So what happens in this case? Here, for example, let us consider these plates. You have the Pacific plate, let's suppose, and on the other hand, let's suppose you have the Filipino plate. Now, Pacific plate is going to be heavier. Now, when they are going to collide, when they are going to converge, again, that motion is not going to be smooth as one plate undergoes subduction. that motion is not going to be smooth. It is going to be rough. It is going to be very staggered, right? Because the other plate will offer significant amount of resistance in between. So that is why whenever there will be a sudden motion, it will accompany a release of lot of energy in the process, which we refer to as earthquakes. So all of this will be covered under water. You have significant amount of water on top, right? Now, in this situation, as the older plate starts sinking down, first of all, there will be a deformation which will happen in the other plate also. The other plate gets severely deformed in the process. Why? Because the motion is not going to be smooth. Now, in the earlier scenario, we had seen that along with the deformation, there is going to be accumulation of materials which would lead to the formation of a fold mountain. But in this case, the oceanic plates are so thin that there won't be any formation of fold mountain due to convergence in the oceanic plates. Continental plates are thicker, so there the materials can get accumulated. Oceanic plates are 5 kilometers, 10 kilometers thin. So that is why there won't be any kind of accumulation here. So that is why no fold mountains. Rather, in this region, you will observe the same scenario where we found out the formation of an oceanic trench. Oceanic trench. Example, Mariana Trench. The deepest oceanic trench present across the globe is the Mariana Trench, right? Its depth is close to around 11 kilometers from the sea surface. So that is formed due to deformity of the crust. Now, after that, along with the presence of the plates undergoing subduction, you will also come across the scenario that some amount of the water also manages to seep in as these plates are going down. Water along with sediments that will seep in. So upon reaching a depth let's say of around 150 to 200 kilometers, the temperature will rise up so significantly that the materials will start melting. And the materials, when they start melting, they will start to rise up. These materials will start to rise up. And these materials, as they rise up, they will be easily able to break through the surface because the crust is much more thinner. So here, it will lead to a volcanic eruption underwater. A kind of a volcanic eruption underwater will be observed. Now, it can happen that, let's say, the plate movement stops thereafter. The plate movement, let's say, does not continue. So if the plate movement does not continue anymore, do you think there will be a further volcanic event in this region? No, because now you don't have the supply of molten materials. So as long as the plate is indicating a movement, there will be the supply of molten materials, and the molten materials will continue to rise as volcanic eruption. So here the eruption happens. Slowly and steadily, this grows larger and bigger in size. Slowly and steadily, this will continue to grow larger and bigger in size. Eventually, as the volcanic events they keep on continuing, a time or a phase will come when it will be able to break through the surface itself. A time will come when it will be able to break through the surface. Now, when it is able to break through the surface, then what do you have? In that case, you have the formation of islands. volcanic islands. Example, the entire region of Indonesia, Philippines, all the islands that you have, they have been created in this process. So, example, Philippines islands. Tonga Island is another example. Even barren islands in Andaman Nicobar. Right. So majority of the regions where you will find the existence of the island, there you will find that the island formation has happened in this particular format, in this particular method, due to volcanic eruption eventually when it increases in terms of the volcanic materials erupting out and cooling down. That is how they emerge as an island. Meanwhile, if let's say in certain places there has been volcanic eruption, let's say the molten materials have traveled through and there is a volcanic eruption which has happened, but it has not risen up anymore. There the volcanic eruption has stopped. So that leads to formation of what are referred to as underwater mountains, and this is what is referred to as sea mounts. Okay, now this zone will be a zone of this zone will be a zone of high magnitude earthquakes. Earthquakes. Okay, these lead to the generation of very high magnitude earthquakes. All around the region of Pacific plate, there is a some or the other convergence happening. And regardless of which type of convergence is happening, the Pacific plate being the heavier one is the one which undergoes subduction. That is why the Pacific plate is shrinking in size. And all around the borders of the Pacific, we have the frequent eruption of volcanoes and a frequent occurrence of very high magnitude earthquakes all around the region of the Pacific. That is why the region around the Pacific is also referred to as the Pacific Ring of Fire, owing to the frequent volcanic eruptions happening due to convergence. Okay. Now, these islands, so the island is floating. How come can we say that the island is floating? The island is very much fixed to the ground or the sea floor, the ocean floor. So, how can we say that the island is floating? Okay. What role water play after pouring through the trench? So when the water tends to seep in, that water will evaporate, or rather will vaporize very quickly due to high temperature, and it will get converted into steam. That will add the pressure which will break through the surface, which will push the molten materials through the surface. Here you don't have a fold mountain formation. Why? Because in this case, you don't have any particular thickness of the plate which can accumulate and form a mountain. Right? In the case of a continental plate, because they were so thick, that is why accumulation could happen. But here the oceanic plates are thinner, so that is why no fold mountain will be formed. Okay? Can water penetrate through the volcanic gap through which molten material comes to the surface? Yes, it can. Pacific Ocean is subduction happening today? Yes, that is what I told you, that even today, the Pacific plate is shrinking in size because it is undergoing subduction from all different sides. Okay. Formation of Andaman Nicobar Islands, we'll talk about it separately when we come to Indian geography. Okay, if volcano becomes inactive in oceanic convergence, then why will it continue to grow? If the volcano becomes inactive, then it will not grow anymore. As long as there is supply of molten materials, till then the volcanic landform will continue to grow. Once the supply stops, it will be reduced to an underwater mountain, a past volcano. So that underwater mountain is referred to as a seamount. Underwater mountain. Okay, so that is the aspect of an oceanic convergence, right? Now, is this the reason for island prone to earthquake? Yes, this is the reason. Water convert into vapor and help magma to come to the surface? Correct. Can these Indonesian and Philippine islands submerged underwater? In the long run, it can, but as of now, they are not indicating any such movement. Okay. You have the Emperor Seamount, which is very, very tall. You have certain seamounts even in the region of Atlantic, which are almost as tall as the Everest, Kishan. Or Amit, that was the question. Kishan, what is called when peak of a seamount eroded? I think that you know the answer, but nonetheless, because you have asked the question, it is referred to as a guyat. We will talk about it when we come to oceanography. Okay. Is Fiji Islands drowning because of this? No. That is drowning because of the rise of water level due to climate change. Western Ghats is not an example of this. Western Ghats is an example of an escarpment. Okay. Then after this, we come to the portion of continental convergence. What is or what happens when you have a continental convergence? Let us understand that. So in this case, there will be almost negligible amount of subduction because both the plates are very light. So because both the plates are very light, there will be negligible amount of subduction. Both the plates are very light, hence there is negligible subduction. And for all of you, I would request, please wait till we finish all the different types of plate movements before you start painting the larger picture that what is happening across the planet. Is this created because of that? Wait for the larger picture. Wait for the entire portion of the plates. Atlantic is expanding, Pacific is contracting. Once you look at the entire picture, you will get a much better clue. So just observe what is happening. So here in this case, we can take the example of Indian plate converging with the Eurasian plate. Indian plate converging with Eurasian plate. Both of them, at the point of convergence, they are significantly continental. So let us understand here what happens. Yes, Indo-Australian or Indian plate, anything that you can consider. So here what happens. Suppose you have one of the light plates. Now, still in comparison to the Eurasian plate, Indian plate is a bit heavier. So some part of the Indian plate does undergo subduction, but in very limited quantity. So here you have another plate. That is the Eurasian plate. Right? Eurasian plate. And you have the Indian plate. They are moving towards each other and they are undergoing a point of convergence here. Now, in this case, both of them are very light materials. Both of them are converging. What will happen? The materials will get compressed. When the materials get compressed, the crust becomes significantly thicker. So that is when you will observe the formation to an extent where the crust folds to form a fold mountain. It will form a fold mountain, right? At the same time, the crust will start to thicken because of compression. The crust will begin to get very, very thick in this region. Now, some part of the Indian plate, which is slightly heavier, that part of the Indian plate will continue to indicate some limited amount of subduction. Very limited amount of subduction will be initiated by the Indian plate. Okay, very limited amount. But here you will come across the formation of fold mountain. Fold mountain, example of that fold mountain, Himalayas, Alps, right? All this are example of this kind of a fold mountain formed as a result of convergence. Now, the crustal thickening in this region happens. Why? Because there is compression from both sides. Yes, Ural mountains are also an example. Now here, compression happens and that leads to crustal thickening. Now, if I ask you a simple question, what do you think will be density of rocks present in this region? In this region, if you consider, what do you think will be the density of rocks? Will it be high? Will it be low? Okay. The density of the rocks in this region will be very high. Why? Because under so much amount of compression, under so much amount of pressure, all the rocks will get metamorphosed and they will be pressed, they will be compressed to such an extent that the materials will be very closely packed to each other. So in these areas, you will come across very high density of rocks due to crustal compression. Now, as some portion of the plate does subduct and also due to other activities, these are also the regions of very massive earthquakes. Here also, you will have very high intensity and very high magnitude earthquakes. Himalayan region is very famously known for the high magnitude earthquakes. The Kathmandu earthquake, which happened in 2015, is nothing but an example of that. Similarly, you have frequent earthquakes happening across the entirety of the region of the Himalayas. So here you will experience a lot of earthquakes and fold mountains. Do we experience volcanic eruption in this? No. Why? Because of certain reasons, a couple of reasons. First reason is that in this case, you don't observe the penetration of water. So there is nothing which will easily vaporize and bring that significant amount of pressure. That is the first reason. The second reason being that even if, let's say, there is a presence of molten materials, the crust above them is so very thick and so very dense that it becomes impossible for the materials to break through the surface. So, for example, we had seen earlier when we were talking and looking at the structure of the planet, we had talked about the fact that the continental crust in the region of the Himalayas can be as thick as 70 kilometers of highly compressed rocks. So that is why no volcanic eruption in the case of continental convergence. Here, no volcanic eruption. Okay. First, no penetration of water as observed in oceanic convergence. Secondly, you will observe crustal thickening makes it impossible for the materials, the molten materials, to break through the surface. To break through the surface. That is why whenever you have continental convergence, there is no volcanic eruption which will be observed in that region. Always keep that in mind. So for convergence, if there has to be a volcanic eruption, it has to be an oceanic plate which has to be involved to bring about that volcanic eruption. Okay. So this is about the convergence and what the convergence of the plates lead to. In the case of continental convergence, the materials, they get crushed, the materials, they get accumulated, they get folded. Hence you have the fold mountain, the crustal thickening happens. Some part of the heavier plate still undergoes a slight subduction nonetheless, and that leads to very massive and highly intensive earthquakes. In the meanwhile, there is no volcanic eruption which will be observed there because of various reasons. So now we take an overall view of the convergences in general. So this is not all the portions of this we have covered till now. So if you take a look at the larger picture, observe this portion. Here you have an oceanic plate and another oceanic convergence. So here, molten materials, they start coming out and they form a series of islands, right? Because the convergence will be happening across a very large distance. Convergence won't be restricted to a small point. It is something which will spread across a very large distance. So that is why series of islands. Near those islands, you will have a trench formation. Here again, there is an oceanic convergence with a continental crust. Observe that the crust folds to form the fold mountain first, and along with that, you have molten materials which start rising up, along with the sedimentary particles, etc. And you have volcanic eruption. Here also, you will have a large trench, right? So that is how you have the convergences which are going to span out. Okay. Now, here, whenever you have the convergence, basically, convergence brings about various different types of landforms. So you have the formation of fold mountains and trenches. This is how the fold mountains appear to look like. Observe this. Observe the kind of folding, a series of folds. So that is how the fold mountains appear to look like. Then you have oceanic trenches. Wherever oceanic convergence takes place, a trench formation will be observed. Then after that, you will also observe the formation of seamounts or underwater mountains, seamounts, and also you will observe the formation of island chains or island arcs. So all these are created as a result of convergence. Nowhere is the impact of convergence as highlighted as the region around Pacific. Around the entirety of the region of the Pacific, there is some or the other convergence happening. Either there is a convergence of ocean continental or oceanic. That is why in the entirety of the area around the Pacific, you will find frequent occurrence of volcanoes. along with the occurrence of very severe earthquakes. That is why the region around the Pacific, that is also what is referred to as the Pacific Ring of Fire. Pacific Ring of Fire. Why? Because all around the Pacific, you have convergences. In this portion, you will observe that the North American plate is moving westwards. So, as the North American plate is moving towards the Pacific region, it will climb over because the plate, North American plate, is a continental one. It will be lighter. Pacific plate, being the heavier one, will get subducted. So here you have North American plate subducting or converging with the Pacific plate. In this region, the Pacific plate is undergoing subduction underneath the Eurasian plate. In this region, it is undergoing subduction underneath the Philippine Sea plate. In this region, around the region of Australian plate, Indo-Australian plate. That is why here you have Tonga eruption and so on. Here Nazca plate is undergoing convergence and subduction. So in various different parts around the Pacific, you have continuous subduction which takes place. That is why the entire region of Pacific is dotted by volcanic eruptions, and hence it is referred to as the Pacific Ring of Fire. Okay, so here Pacific Ring of Fire is frequent occurrence of volcanoes all around the Pacific Ocean due to convergence and subduction of oceanic plate. Okay, that is how you have this Pacific Ring of Fire. Now, this question about what happens in Pacific Ring of Fire, this has been asked by UPSC multiple times in the general studies. It has been asked by UPSC multiple times even in the portion of optional area of geography. And this is one of those areas where UPSC is not afraid to repeat the question. So the same question has been repeated oftentimes, that what is the incident of Pacific Ring of Fire? Explain the geophysical characteristics of Pacific Ring of Fire. Why you have volcanic eruptions in the Pacific Ring of Fire. So as a candidate, all you have to write out along with the schematic diagram is what are the various subductions which happen, what happens in the case of a continental oceanic convergence, what happens in the case of an oceanic convergence, and how each of them can lead to volcanic eruptions. Just explain this portion and your answer is good to go. You will get very good marks in that. Okay. Now, then we come to the portion of Indian plate, its movement, and the formation of Himalayan mountain range. So when we talk about the Indian plate, long time back, around 150 million years back, basically, you had the situation where Indian plate, African plate, South American plate, Antarctic plate, Australian plate, all of them were together. One landmass placed very close to the region of Antarctica, Gondwana land, as it was referred to. Now, around 120 million years back, these land masses, 120 to 130 million years back, these land masses started to break up and started to move away from each other. Why? Why will the land masses move away from each other? Not because of what Wagner had said, but because of the simple aspect that whenever you have the convection current inside, that convection current will push the lands away from each other. Just the same concept as why the plates move after all. The same concept. So the plate started moving away. Here, the Indian plate started marching north. Now, at that point of time, Indian plate was moving at a very swift speed. It is estimated Indian plate's movement at that point of time was amongst the fastest across the globe. And Indian plate was moving somewhere between 15 to 20 centimeter per year. That was the rate of motion. But still, it means that in order to cover, let's say, a few kilometers, it did take thousands of years, nonetheless. But it was moving. And it was moving to the north. And it was moving to the north where, if you consider this as the planet, basically, if let's say this is the equator, here you had the Eurasian landmass, the Eurasian plate, right? And Indian plate, it started moving northwards. It started its march north. It came significantly northwards here. There were multiple events which happened in between. Madagascar got separated from the west coast of India. There were volcanic eruptions which happened in between, etc. But that is a topic for another day. So, here, as it started moving north, it encountered a water body in between them. And that water body was a kind of a shallow sea that was named as the Tethys Sea. Tethys Sea. This was your Eurasian plate. Okay. Now, here, basically, as it started moving north, it encountered the Tethys Sea. Now, Tethys Sea will have an oceanic crust. Continental crust will be present in the Indian plate and the Eurasian plate, isn't it? So, this Tethys Sea, having a kind of an oceanic crust, underwent some amount of subduction. As the Indian plate was pushing it, the Tethys Sea underwent a subduction in this particular region. So, when the Tethys Sea underwent subduction, there were volcanic eruptions which occurred in this area. And some folding also occurred because it was a typical oceanic continental convergence. But the rate at which the Tethys Sea was undergoing subduction, that was slower in comparison to the rate at which the Indian plate was rushing towards it. I will repeat. The rate at which the Tethys Sea was undergoing subduction was much, much slower as compared to the speed of the Indian plate. So imagine that the Indian plate was rushing in. Tethys Sea was not subducting at the same rate. So what would be the outcome of it? Eventually, the Tethys Sea was compressed. And when you compress the portion around the ocean, what happens to the sea floor? The sea floor is thrown up. There was an upliftment of the Tethyan sea floor. And with the Tethys Sea out of the picture eventually due to that upliftment, then you had a complete continental convergence. And that continental convergence further accelerated all the folding which was present earlier in the Eurasian plate, the folding which was created due to the uplift of the Tethyan sea floor, and the newer folding initiated. Now, this created the chain of mountains that we know as Himalayas. As we talk about, the Indian plate is still moving northwards. But now the speed has reduced to around 1 to 2 centimeter per year. But the movement is still there. Now, because the movement is still there, that basically means that there is still a continued folding which is happening. It is that reason why the Himalayas, they are still rising in height. It is that reason why when you observe the fold of the Himalayas, the fold of the Himalayas are changing shape. They are basically becoming narrower at the bottom and taller, which means what? There is something which is compressing them from both sides. And it is because of that movement that till today, that is a region which is very, very much earthquake prone. You have very frequent seismic activities in the Himalayan region. So that is how the tallest mountains of the world have been created. Now we will basically break it down, the entire story of it, in various different stages so that it becomes easier for you to consume. I read that Tethys Sea consume from both sides. Please tell. Okay. Why the speed has reduced? I'll come to it. Can you please repeat the upliftment of Tethys Sea again? Okay. What could be the reason for Deccan traps? What are Deccan traps, my dear friend? See, I many of the times when I take a look at the question, I get an understanding. Any faculty or any teacher gets an understanding about the aspect why that question has been asked. So rather than going into the details of it, that why certain questions are asked, let me just humbly submit in front of you. It will be much better if we wait for when the topics are going to be picked up. As of now, whichever portion is covered, let us concentrate on that. Let us ensure that we understand everything in that particular topic. Slowly and steadily, just wait. We will cover all the aspects. What is Deccan traps, how they are formed, how they are created, everything we'll be talking about. But let the time come. Now, this question has been asked because we mentioned Reunion Islands. Because I'm sure the individual who has asked the question, they will also be knowing the answer to it. So you just need a kind of a confirmation bias that, okay, that person has confirmed, I knew this, now I feel better. Please let's not get indulged in these kind of minor plays. We are preparing for civil services examination. A minor thing here and there, a minor joy here and there, that should not be sought after. Okay? So here we take a look at the entire aspect of the formation of Himalayas one by one step at a time, right? So let us take a look at it. Formation of Himalayas. Of Himalayas. Okay. So how the formation happened? So the first stage was basically movement of the Indian plate. Of Indian plate. Now, when you had movement of Indian plate, you had a situation where, let's say, the Indian plate had initiated a movement and it was moving towards the Eurasian plate. Now, in between these two, you had the presence of the Tethys Sea. As the Indian plate was pushing ahead, the Tethyan sea floor underwent subduction underneath the Eurasian plate significantly. Minor portion got subducted underneath the Indian plate as well, very minor portion. But a major portion underwent subduction underneath the Eurasian plate. It is estimated that close to 5,000 square kilometers of the Tethyan Sea floor underwent subduction underneath the Eurasian plate. You had this as the Eurasian plate, this as the Indian plate. Now, at this point of time, the speed of movement of the Indian plate was roughly around 15 to 20 centimeter per year. It had reduced to 15 centimeter per year by the time Tethyan subduction started, but let's assume 15 to 20 centimeter. Eurasian plate has always been very steady, very chilled out, and that is something which you find even today. Eurasian plate since that point of time was moving at around 1 to 2 centimeter per year. Okay, now here after this, comes the second stage. Now, by the way, when you had this subduction happening, you had a volcanic eruption happening here also, and few volcanic eruptions happening on the front of the Indian plate also. Now, before we come to the second stage, the rate of movement of the Indian plate was much faster as compared to the rate at which the Tethyan seafloor was undergoing subduction. That is why eventually the Tethyan seafloor, due to compression, was pushed up. Let me write the reason here so that you have a recollection. Rate of movement of Indian plate is much faster, or was much faster, as compared to the subduction of Tethyan seafloor. As a result of that, due to continued compression, Tethyan seafloor was pushed up. It was, in a way, compressed, and it crumpled like a piece of paper, and it simply upfolded. So that is where you had the second stage. That is what is upliftment of the Tethyan sea floor. Upliftment of Tethyan sea floor. Why did the upliftment happen? The reason of this I have mentioned here. Okay. Now, the upliftment of Tethyan sea floor, when it was initiated, at that point of time, the Indian plate speed reduced because the Tethyan sea floor started rising up, getting folded up. And between the Indian and the Eurasian plate, some portion had gotten compressed, right? So the crustal thickening had started happening. It is during this stage that even the Tibetan plateau was created on the side of the Eurasian plate. The Eurasian plate was already getting compressed. Tethyan seafloor was subducting underneath. There were molten materials which were present. Everything started getting compressed, started increasing in height. And that is when the high altitude plateaus of Tibet at that point of time were also created. And that is why till today, if you look at Tibet, it has got many high altitude lakes, Many of them are said to contain water which was uplifted. The entire floor was uplifted during the upliftment of Tethys. So many of them are said to contain water which has been prevalent since the time of the Tethys Sea itself. So it is during this stage that the Tethyan Sea floor basically started rising up. It was pushed up. It was compressed. It was pushed up. You had crustal thickening, which happened more significantly towards the Eurasian side because that is where significant compression had happened. So this was the Indian plate, and this was Eurasian plate. And this was the uplifted Tethyan sea floor, this portion. Now, by this time, the speed had reduced. Speed of Indian plate had reduced to around 10 centimeter per year. Now, after this, the Indian plate was still moving at a speed of 10 centimeter per year. So, after this, what ensued was a pure continental convergence. You did not have any seafloor in between. So, because the seafloor had been uplifted. So, after this, what followed was a pure continental convergence. So, the third point is continental convergence. It is here that the Indian plate crashed with the Eurasian landmass, including everything that the Tethyan seafloor, etc., which were in between, and you had a cumulative folding which started happening. So that is when you had the formation of a fold. The first fold of the Himalayas were created. But the Indian plate continued to move. Now, when you have this convergence between the continents, the pressure is so very high. Oftentimes, at the point of convergence, the temperature also becomes very high. And in the case of very high temperature, the rocks, they start welding together. They start becoming one material. So oftentimes during this convergence, the materials, they get welded together. So that is where here basically observe that the movement continued. And as the movement continued, the compression continued, means the height continued to increase. Now, all these are rocks which are getting deformed. Now, rocks, they are not like a piece of paper that you can deform them as much as you want. The rocks that you see out in the open, they are so very solid. So they have a kind of a deformity limit, an elastic limit. If you try to deform the rocks beyond their elastic limit, what happens? What do you think will be the outcome if you try to deform the rocks beyond their limit? Very simple. Rocks will break. They will rupture, isn't it? So here, as the compression continued to happen, it is in these areas where there was immense stress in the rocks which was observed. And immediately after that, beyond a point, the rocks, they break. So that is how you have development of cracks in these areas. So that brings us to the fourth point and the fourth stage. So this continental convergence, by the way, this happened close to around 55 to 60 million years ago, somewhere between 60 to 55 million, 50 million years ago. In that 10 million year gap, that is when this was happening. Then we come to the fourth stage, development of crack and the rise of Himalayas. Now, this is a portion which is interesting as well, and also very important to understand if you want to understand how the formation process basically panned out. This is very important to understand. So pay attention here. So here, compression was happening. As the compression was happening, there was a development of a crack because the rocks could not get deformed beyond an extent. So you had a crack. And meanwhile, a continued push, a continued compression means the height continued to increase. Right? A continued compression meant the height continued to increase. Now, this crack, it is in this region. If you observe the region around the crack, A region where a crack exists, that is also what is referred to as a fault line. So that is what is also referred to as a fault. So it is across this crack or fault where the rocks, due to the compression as the Indian plate was moving, the Eurasian plate was moving. What do you think? Will there be slight movement of the rocks here or not? There will be a movement of the rocks. And this movement, it will not be regular. It will be staggered, irregular, because it will experience resistance from the other rocks in that region. So that triggers massive earthquakes, very massive earthquakes. But as the land continues to push, the rock will not continue to move against the other rocks continuously. There will be a folding of the land. So there you will observe land starts to get folded. Right? So that is when you had the creation of the other ranges, formation of other ranges. So because of increased compression, now beyond a crack, another range started coming up. And that range was formed around 25 to 40 million years ago, in that time interval. In the meanwhile, you already had the existent mountain, which was very tall. Okay? The existent mountain, which was getting taller by the day. And this is where you had the crust, which began to get thicker. Now, the compression continued for a few million years. For around 10, 12, 15 million years, this continued. Now, as the process continued for around 10 to 15 million years, what happened? This started to increase in height. It started getting narrower at the base. But here also, slight movement was observed here. Whenever there was any kind of movement, it triggered massive earthquake. Now here you might have a curiosity that why did a crack develop only on this side? Why didn't a crack develop on the other side of it? What do you think can be the reason? The reason is very simple. It was the Indian plate which was pushing ahead all along. So that is where the deformation happened very significantly and very starkly in front of the Indian plate, not in front of the Eurasian plate. That is why even today, if you take a look at the Himalayas, the southern slope of the Himalayas facing India is much steeper, whereas the northern slope facing the Eurasian plate, they have a gentle slope because it is the Indian plate which is pushing in. So here, basically, that is how you had the development of a second fold. But once you had the second fold, this would also get deformed, isn't it? This would also get deformed beyond a point. This also has got a deformation ability, just like the third and the fourth point. Here also something same will happen. So here, again, this portion underwent or experienced huge amount of stress. So here also, you had the development of a crack or a fault. And that brings us to the final stage. That is formation of the final range, that is the Shivalik. Formation of Shivaliks. So just like in the fourth point, here also think about it. The compression is still happening, even though the speed by this time had reduced massively to around 4 to 5 centimeter per year only. But here, basically, the convergence is still happening. And as the convergence is happening, what will be the after impact of it or the after effect? The existing mountain range, they will start getting taller because the entire process is getting converged. Now, there will be slight movement here and here as the rocks try to adjust themselves. That will lead to massive earthquakes in these areas. And also, this particular portion now, right, beyond the crack, like it was in this case, right? So, similarly, here also, the portion in front of the crack, that will again experience compression. So, here again, you will have compression. So, for example, this will lead to formation of the Shivaliks, the mountains formed earlier before that is the middle Himalayas, the Himachal, and then you have the tallest of them all, Great Himalayas or Himadri, which till this point of time has become extremely narrow because of continued compression that it has been facing. Now, in this region, it is a continuous kind of compression or continental convergence. That is why no volcanic eruption in this place. And still today, the Indian plate is moving northwards. But now the speed has reduced to around 1 centimeter to 2 centimeter every year. So the rate of folding has reduced, but the folding continues nonetheless. And this is why the height of it continues to increase. Now, the beauty of this subject is that if you know what happened in the past, if you know what is happening right now, you have the ability to predict what is going to happen in the future. So, while we cannot predict what life will be or whether life will be present, human life will be present, etc., in the near future, we can predict what is going to happen here in the future. How? So, here, the latest developments have indicated, and latest researchers have indicated, that there has been a development of a new fault line, a new crack here in this region, before the Shivaliks, in front of the Shivaliks, that is. That means going ahead into the future, we can expect that there will be a fourth range of Himalayas coming in front of the Shivaliks. So, in the present day region of northern Uttar Pradesh, the present day region of northern Bihar, the present day region of North Bengal, and the region of North Assam, we will have a fourth range of Himalayas in the coming future, in the nearby coming future. But again, when I say nearby coming future, for geography, that is very different as compared to the other subjects. For other subjects, nearby future can mean next year, 20 years down the line, 50 years down the line. Here, when we say nearby future, we are referring to 5 million years down the line. 5 million years, 10 million years down the line, there is going to be the formation of a fourth range. That is why nowadays you will observe majority of the earthquakes, they are happening either in this region, across this fault line, or across this fault line. Kathmandu earthquake which occurred happened because of movement in this crack. The very infamous Bihar earthquake which occurred in 1934 happened across this one. The recent Assam earthquakes which occurred across these areas. So that is how basically the formation of Himalayas has panned out. I hope this is understood. Steep and gentle slope, basically whichever portion is compressing, that is the portion where you have this steeper slope. When we come to the Indian geography and Himalayas, we'll talk about it. It is referred to as a hogback topography. Okay, right? First range is more continuous, other are broken, because that is where the speed had also slowed down and the convergence was not very uniform, because the Indian plate by that time had started basically pivoting. And that is where the formation started happening in the eastern part and northeastern part. Okay? Yes, Pulkit. They were also created in this manner. What about the ice in the Himalayas? What about the ice? Okay, do you mean to ask that how that ice is created? Okay, I understand what the imaginations would be in the mind, that Tethys sea water would have risen to that level and they have frozen, but no. When the height increases beyond a point, temperature drops so sufficiently that water cannot exist either in liquid or in gaseous state. That is why you have the presence of ice in that region. That is why that region is frozen. What happened to the older Himalayas? The older Himalayas are still there. That is present. That is the Great Himalayas. Okay. This means that formation of new ranges after the fourth range will continue in the future. Yes. But depending as long as the Indian plate is going to move. Okay. What happened to the water of the Tethys Sea? Water of the Tethys Sea basically drained out from the sides of it as the Indian plate was moving north. This was a slow movement, so the water drained out from the sides of it. Why will the water stand accumulated? In certain areas, that water has been trapped in few of the inland lakes. Okay. There will be question like predict the future natural process. No. Can you explain again the entire process? Do you want me to explain the entire process again? Okay. Do we have any ambition to move in the next topic, or do we want to stay for 24 modules in the same topic itself? As of now, the speed of Indian plate is around 1 to 2 centimeter per year. Fourth point is basically when you have increased amount of convergence basically means there will be increased deformation, but the land cannot get deformed beyond a point. The crust cannot get deformed beyond a point. That is why you have the development of the cracks. So these cracks developed here. Furthermore, as the compression happened, there was some movement of the cracks here, but that is where the folding of the land began in the region in front of the cracks as well. Okay, right? So now we move to the basic concept of it. That is, the Tethys Sea eventually was uplifted. It is an ongoing motion, and that is why the Himalayas are still rising in height. And you have, because there is movement and instability of plates, that is why this is the region which still experiences very heavy earthquakes. Okay. You written wrongly as oceanic crust in the reason for no volcanic eruption in the previous slide. Where did I do that? Which slide? No occurrence of volcanic eruption. Where is the mistake? See, it is always very easy to perceive that the faculty has committed some or the other mistake. Please never try to test that. Okay? Please never try to test that. Even if you get the what is the correct information, fair enough. Where is the mistake here? Let me know. And then we will move forward. Ashwant, before that, we won't move forward. Let me know where is the mistake. Jyoti, what about the portion about frozen? So here, when we talk about the frozen ice that you find on top of the mountain, so basically, see, the height increases beyond a point, the temperature will be very, very low. So in that low temperature, water vapor will not exist. It will exist in liquid or solid form because there will be condensation on the surface. That is why those regions experience significant amount of snowfall and icefall. That is why we have the presence of ice. The uplifted Tethys Sea is present in the region of the Himalayas itself. Is there any doubt in that? Ashwant, you have not clarified as of now. You written wrongly as oceanic crust as the reason for the volcanic eruption in the previous slide while explaining. I had written here that in this case, basically no penetration of water will take place as observed in oceanic convergence. In the case of oceanic convergence, do we observe penetration of water or not? In this case, we don't experience the penetration of oceanic water. So that is why here you don't have volcanic eruption. Is that clear? Right. Okay. Now we come to the portion of divergent plates. What happens when the plates move away from each other? So basically, divergence is again created by the same convection current. The convection current basically that pushes the plates to move away from each other. So when you have a divergence which is observed, divergence also oftentimes not only means parting of the plates away, but the convection current will bring newer materials to the surface and they will solidify to form newer crust. So that is why, because there is a construction of a newer crust, this is also what is referred to as a constructive plate boundary. Constructive plate boundary. Because there is a creation of a newer crust. Now, this convection current generally is observed wherever, eventually we have seen that wherever the convection current is observed, that region becomes very, very thin. Eventually, water pours in and penetrates from the other areas. That region gets underwater. And that is where eventually there is a creation of a mid-oceanic ridge underwater. It continues to move away. But does not mean that under land there won't be a convection current. Under land also there can be a convection current. But the land will start parting, it will form a very deep depression, water from the nearby ocean will come in, that region will also become a water body, and there will be a mid-oceanic ridge there also. So when we talk about the divergence, here you will observe that this divergence happens. In the case here, you will observe the mid-oceanic ridge underwater. That is where the convection current is in action. And it is here that the newer crust is created and the older crust is pushed aside. But when we have the convection current, let's say underneath the land areas, what happens? You have a development of a rift valley. What is a rift valley? Rift means there's a tension. Valley means there's a depression. So when you have the plates moving away from each other, there's a kind of a tension. And as the plates are pulling away from each other, there will be a depression. Observe this large crack that you see on the ground. This large crack that you see on the ground, just to give you an idea about the size of it, the scale of it, all these small white things that you see, all these small ones, these are as large as three-storied bungalows, right? Around a lake. This is a tourist spot. So this is what is the East African Rift Valley. We can also say fissure, that is also correct. So this is example of East African Rift Valley. In many of the cases, what happens is that as this Rift Valley starts to develop, right, eventually, or as this mid-oceanic ridge starts to develop, as this divergence starts to happen, molten materials, they are thrown to the surface. But these molten materials, rather than what you think about a volcano, that molten materials will come out from one point, you have a special kind of volcanic eruption which is observed, and that is a fissure volcano, where the volcanic materials, they emerge out of a very large crack which appears on the ground surface, right? So you have a very large crack which develops on the ground surface, which is a fissure, and you have molten materials which start erupting out, which start emerging out. Example is what you observe in Iceland. In Iceland, you have very frequent type of these eruptions. We will refer to it again when we talk about volcanoes in detail. So example, Iceland. Okay. So here, look at these. These are your mid-oceanic ridges across the world. It is here that divergence is happening. Now, across the entirety of the Atlantic, observe that divergence is indeed taking place. Divergence is indeed happening here. Now, the fastest rate of divergence as of now is happening in this region here in the Pacific, between the Pacific plate and the Nazca plate. So, this region, which is also referred to as the East Pacific Rise or the Chilean Rise, East Pacific Rise. This is where the rate of divergence is around 15 centimeter per year. So that is where newer crust is getting created, right? So wherever divergence is happening, newer crust will always get created. Observe there is a continuous divergence happening across the region of Atlantic plate. That is why Atlantic plate continues to become larger and larger and is still present in the region of the South Pole itself, right? So that is basically the aspect of divergence. This divergence, which has happened across the region of Atlantic here, the molten materials have come up as volcanic eruptions. They have accumulated to form the entire region of Iceland that lies on the mid-Atlantic ridge, the mid-oceanic ridge. Observe, this is the boundary. This is the boundary between the American plate, North American plate, and the Eurasian plate. This is the boundary which exists. So you have volcanic eruptions happening there, newer crust getting created there, and that is how eventually, as it mounts up, you have the formation of an island almost. That is why Iceland is so very frequented by volcanic eruptions. Volcanic eruptions are very frequent in the region of Iceland. Okay? Then we come across the transform plate boundaries. Transform plates, these are the plates which move parallel to each other, right? They don't move towards each other, away from each other, but they move parallel to each other. For example, if I give to you the example in this situation. So observe here in this portion, the northern portion is moving in this direction. Eurasian plate is moving in this direction. In this portion, you have divergence as well. But both these divergence, the rates of divergence which are spread across thousands of kilometers, the rate of divergence, will it be same? Obviously not. One portion will be moving at a different speed as compared to other. So that is when, as the two plates are moving in the same direction, but one is moving at a faster, other at a slower speed, there happens to be a development of a crack. And then we have the parallel movement. So that is what is the transform movement. So when we talk about the transform plate movement, this happens parallel to each other. So here you have the parallel movement. So in this, neither a crust is created, neither a crust is destroyed. So this is also what is referred to as a conservative plate margin. It can be moving in the same direction as well. It can be moving in the opposite direction as well. So that is why it is referred to as conservative plate margin, because it neither creates a new crust nor does it destroy an old crust. Now, after this, as these plates are trying to move parallel with respect to each other, will the movement be smooth? Never. So, due to the resistance offered, oftentimes there is development of very large and extensive cracks. Development of very large and extensive cracks. And it is across these cracks that you have massive earthquakes, very massive earthquakes, which are experienced. For example, you have the San Andreas fault or crack, which is present in the region of California. That is because of the transform movement. That is why California is a region which experiences very massive earthquakes. So this is basically why you have creation of fault lines, which are also referred to as the transform faults. Right? Development of cracks. So these become example San Andreas fault, where California, in the region of California. Okay. So that is the case with transform plate boundaries. So the plates, they move parallel to each other, neither creating nor destroying a feature. It leads to significant tension being built up and creation of earthquakes and faults. This is a conservative plate margin, means neither a new crust is created nor a crust is destroyed. So neither a creation of new crust nor a destruction of the older crust. So that is why conservative plate margin. Conservative plate margin. Okay. So that is the case of the plate movements and the plate boundaries. So here you get a kind of a delineation, a kind of a mapping of the entirety of all these plates along with the plate boundaries and the direction in which they are moving overall. Right? So here, if you will observe, look at the Indo-Australian plate. These are the major plates that you have. Now look at the Indo-Australian plate, this entire region of Indo-Australian plate. Now researchers indicate that this is breaking from here. So in the next few years, in the next few million years, chances are that the Indian plate might completely break away and Australian plate might get separated. After all, the Australian plate is also trying to move north. Indian plate is also trying to move north, but they are moving in a separate manner. Now, as we speak, the land of Africa, that is dividing into two. Here you have development of Rift Valley. So the future prediction is that this portion will be separate and this portion will be a separate landmass. Now, African landmass is moving northwards and it is crushing the region of the Mediterranean Sea. That is why in the southern portion of Europe, you have so frequent earthquakes and volcanic eruption, because it is the Mediterranean Sea which is undergoing subduction. That is why in the future, it is expected that in the region of Mediterranean Sea also, you will have the same fate or the same final result as observed in the region of the Himalayas. Here also, you will have the water finally extinguished, water drains out, and after some point, you will have continental convergence. There also, you will have a formation of a fold mountain. Now, observe in all these areas, you have very frequent earthquake activities, all the plate boundaries. This is why the region of Gujarat also is frequented by earthquake activities. Why? Because Gujarat uniquely stands at the margin, at the boundary of three plates. One is the Eurasian plate, another is the Indian plate or the Indo-Australian plate, and the third is the Arabian plate. So Gujarat lies at the boundary of three different plates. That is why any movement across any of these plates will trigger massive earthquakes in this particular region. That is why Gujarat often is frequented with very massive earthquakes. Okay? Now, that is basically the entire aspect of the plate movement. Very briefly, but don't get the habit of it, because this is not possible to be done in every portion. So very briefly, a kind of a summary. Okay, plate movement Why? Because of convection currents. Due to convection currents in the interior. In mantle. Types of movement. You have convergence. Convergence is of three types. Oceanic-oceanic, will lead to what? Volcanic eruption, earthquake, formation of islands, underwater mountains or seamounts, and trenches. Then you have oceanic continental. That will lead to fold mountain, trenches, earthquakes, and volcanoes. Then you have continental convergence. This gives rise to fold mountains, and earthquakes. No volcanic eruption. Right? After that, we have divergence. Divergence of plates. That divergence creates a rift valley, mid-oceanic ridges, sometimes islands, example Iceland as an example of island, and also fissure volcanoes. Then after that, we have transform movement. In that, we have development of transform faults. You have heavy earthquakes. The arrows indicate the direction of the movement. Okay, this is basically the aspect of all the various different types of movement that you have. Okay, so that is the summarization. Now, a couple of questions from the previous one. Which of the following phenomena might have influenced the evolution of organisms? So, when we say evolution of organisms, basically that means that changing conditions, changing climatic conditions have helped the organisms evolve, adapt to the changing conditions. That is evolution. So, which of these phenomena bring about evolution? So, when we talk about continental drift, that brings about the changing climatic condition, right? So there also evolution happens. When you have glacial cycles on the planet, that is, you have the condition of ice age and again a melting period, there also climate changes quite frequently. So that is where also you have evolution. So that is why in this case, both 1 and 2, that is C, that is going to be the correct answer. Both of them are responsible for evolution of organisms. Then, which of the following pairs is or are correctly matched? So in this case, I will launch a poll so that your inner feeling for that inner joy of getting the right answer, that you tend to feel. So here, give the answer. Yes, yes, I have launched the poll. You get to play your own level of Kaun Banega KBC in general, right? So that gives a lot of joy. No, tsunami is created due to underwater earthquake, Kirubagar. Good. Majority of you have given the correct answer. Continental drift was provided by Alfred Wagner, so this is incorrectly matched. Expansion of universe was provided by Edwin Hubble. This is also incorrectly matched. Photoelectric effect was provided by Albert Einstein. This is correctly matched. So the correct answer is going to be B. That is 3 only. Okay. So 3 only. Then in the structure of planet Earth, below the mantle, the core is mainly made up of which of the following? Fissure volcano, don't worry. Kishan, we will study again in detail when we talk about volcanic eruption. That is when basically a large crack opens up and molten materials, they emerge out of those large cracks continuously. That is fissure eruption. Yes, Pulkit, that is an example of transform boundary, the Anatolian plate that you have in the region of Turkey, which caused that earthquake. Okay, good. Majority of you here also have given the correct answer. That is C, that is iron. Okay, so that marks the end of this particular module. And can we say in conclusion that Himadri is formed due to the upliftment of Tethys Sea and other ranges due to no? Himadri is also formed as a mixture of both of them, both as an upliftment of Tethys Sea as well as the convergence. And all of those happens. Okay. And Mahima, recent Turkey earthquake. So, in the region of Turkey, you have an earthquake which has occurred recently. That is because here you have a minor plate, which is the Anatolian plate. Here you have the minor Anatolian plate. So, there you have a transform movement which is happening against the Arabian plate, which oftentimes initiates a lot of frequent and massive earthquakes in the region. And right. Then I have a question from Pintu. I'm working professional, so I have a very limited. How can I manage time because I give the exam in 2024? So, see, right now you have to, as of now, just focus on reading current affairs on a daily basis and covering the portions that you have covered in the class. Revise it on your own. Give 20 to 25 minutes. Do that religiously and try to gain maximum out of the weekends if you are a working professional. So, all automatically within a month or two, you will see the results. You have to initiate the portion of optional study also within next couple of months so that the optional and the GS can be completed by end December. Okay. And how Eurasian plate was present in northern hemisphere due to the formation of it. So if uh, if you think about it, let me tell you a very brief concept. It will take a couple of seconds only. And that is the concept which was basically highlighted by Tuzo Wilson. And that is what is referred to as Wilson cycle. Wilson cycle. Now, what Wilson cycle tells us about is the fact that every few 100 million years, all the lands they get together, to form a supercontinent. And again, after a few million years, they will break down into many small parts. They will start moving away. Again, after a few million years, all of them, due to various movements, they will come together. For example, right now, North America is moving westward, Pacific is shrinking, Atlantic is increasing. Eventually, after let's say 100, 120 million years, again, you might have a scenario where all the landmass is one. So before Pangea, the planet has experienced two supercontinents, the earliest one being Rodinia, and then the latest one being Pangea, which has broken down into Laurasia and Gondwana land. So again, going ahead into the future, that will come together. Again, it will get broken. Okay, so that explains to you why you have the different distribution of land masses in different ways. Yes, that means that Wagner's concept is justified. That is why continental drift theory is kept in such high regards. Okay, so that will be where I will bid you goodbye for the week. So, here, please revise the portions that we have covered. This will form the bulwark or the base for your all the portions of geomorphology. And please take up the questions which will be uploaded. The subjective questions, 5 subjective questions will be uploaded. Take up those questions for writing. Try to write the answer for them. And there will be 20 objective questions which will also be there. So there also you can take those questions, try to gauge out how much you have understood. Okay, right. And in case of divergence, Raghav, in African Rift Valley, why no fissure volcano like? So not always you will have fissure volcano, but there you have Mount Kilimanjaro in the region of the East African Rift Valley. So volcanic eruptions do happen there. Okay, and please clarify, in case of continental divergence, result will be fissure volcano or penetration of water due to subsidence of land. Generally, it is penetration of water in the region of the formation of Rift Valley, as is observed in the formation of the case of Red Sea. Yes, the class is over. Now you can leave. How transform boundary creates fault. So think about it. When you have two large rock surfaces, when they try to rub against each other, they will develop a large crack, a large fault line. So why? Because the rocks will experience resistance. They will offer resistance to each other. That is when they develop a long crack or a large fault line. Okay. Mains questions. We will give you 5 questions tomorrow. The BHLP subjective test that you have to appear for. So try to take up that test as a test of how much you have understood. Don't worry about the marks at this stage. Let the marks be 0. At this stage, the effort should be to gain as much feedback and input from the evaluators for your answers so that you know which direction to move into. Use as many diagrams as possible. Amit, no, Joshimat crisis is a different aspect altogether. So I think we have uploaded YouTube shorts about Joshimat crisis, why it happened. A point by point explanation is there on YouTube on our channel. Just search it. It is a 1 minute shorts. It won't take much of your time. Yes, Ashwarya, transform boundary also creates a lot of earthquakes. How to draw the ring of fire in exam? So just draw the rough diagram of the region around Pacific. And rough diagram means just draw the rough diagram. For example, demarcate the regions as Australia, show the island regions, show the particular portion around the Pacific plate. Just indicate in the rough diagram, more than sufficient. Yes, Pulkit. Okay. So I think that I have managed to answer most of the questions. How to cover geography if I'm weak in vocabulary? See, vocabulary, my dear friend, is something which you develop slowly and gradually. Vocabulary doesn't come in a day, right? So read as much as possible. And this subject of geography, I will try to deal it in as simple language as possible. So there, one thing you can be assured of from my side, even though you had people asking questions about it, but here we will not commit mistakes, at least in English. That is something I can assure you. So just being exposed to English will automatically improve your vocabulary. Don't worry about that. uh, what is the reason behind the speed of Indian plate to 15 to 20 centimeter per year? See, the reason is a bit complex. The reason is a bit complicated. As the Indian plate was moving northwards, in the region of South Indian Ocean, the Indian plate came across the Reunion Island region. where you have a lot of magma, lot of volcanic eruption. So over that, there was a kind of a smoothening. Frictional force was reduced, and that is what sped up the movement of the Indian plate. Okay, right? How is Indian plate older than the Eurasian plate? So see, different portions have been created at different point of time. Researches which have been submitted in December 2021 indicate that the region of Chota Nagpur Plateau, particularly the Singhbhum region, might altogether be the first landmass created on the planet. So you have different places created at different times. But Indian plate is heavier because of the types of volcanic eruption which has occurred there, the basaltic rocks which dominate there. Can we say that convergence plate boundaries are partially the constructive in Ush? No, no. Newer crust doesn't get created, so no constructive. Is answer writing need advanced knowledge of English? No, answer writing needs basic understanding of English. Your English should be lucid enough, in the sense it should be comprehensible, right? What you are trying to convey, that should be understood. They are not searching for the next Shashi Tharoor. They are searching for the next IS officer who is able to communicate properly. So that should be the aim. Okay. So next we will cover the portion of earthquakes and volcanoes, which will be a natural follow-up of this. Overall surface of Earth remains constant in terms of size, yes, but the morphology keeps on changing. There is a theory in geography which tells that for every height created, there has to be a depth created as well to maintain balance, what is referred to as isostasy. For general studies, you don't have to study that, but overall understand the balance on the surface is maintained. Okay. Where did the Tethyan sea crust go? Is it a part of the greater Himalayas? In some portion, yes, Deepika. And how do we get to know about it? In the region of the Himalayas, you find evidence of marine fossils. So, fossils of animals which could have stayed only underwater. How is it to be found so many meters above sea level? That is the folded Tethyan sea floor. Okay. And Saurav, I cannot understand the introduction. And see, introduction has to follow directly from the question. What is the requirement of the question? Answer that in introduction. And then basically, conclusion has to be the brief summarization of what you have written. Try writing it out slowly and steadily, you will get better at it. Okay. So that is where we'll end the session here, guys. The SMEs are here to answer your question. Any question left unanswered, feel free to get in touch with us. Until we meet again, all the best. Take care of yourself. Goodbye. And thank you for the patient hearing. Hope this session has been helpful to you. Hope you have extracted something positive out of it. So, till we meet again, goodbye and relax. And please do revise the portions that we have covered. Thank you.